In this session, we've curated a collection of the most mind-expanding theories known to humankind. Each concept will be presented in an accessible way, enhancing your understanding and sparking curiosity. The ideas in this session will gradually become more complex as we dive deeper into the concepts. The holographic principle. Imagine walking into a room with a vast collection of books, each filled with detailed information. Yet, what if you discovered that all the information in these books could be encoded on a flat surface like the walls of the room? This analogy offers a glimpse into one of the most mind-bending ideas in theoretical physics, the holographic principle. At its core, this principle suggests that everything we perceive in 3 dimensions may be encoded on a 2-dimensional surface, much like a hologram. The concept, although abstract, arose from a pressing problem in theoretical physics that involved black holes. In the 1970s, physicists Jacob Bekenstein and Stephen Hawking noticed a peculiar relationship between black holes and entropy, the measure of disorder or information contained in a system. Bekenstein proposed that the entropy of a black hole isn't proportional to its volume, as one might expect, but instead to the area of its event horizon, the boundary beyond which nothing can escape. This discovery was shocking because it suggested that the information describing everything that falls into a black hole could be encoded on its surface area, not its volume. This is where the holographic principle begins to emerge. In the 1990s, the physicist Leonard Susskind and others took this idea further. They proposed that the same principle that applies to black holes might apply to the entire universe. In other words, all the information in our seemingly 3-dimensional universe could be encoded on a distant 2-dimensional boundary, much like how a hologram stores a 3D image on a flat surface. Just as a hologram creates the illusion of depth, our universe might be an illusion of 3 dimensions projected from a lower dimensional reality. This idea is deeply tied to string theory, one of the leading candidates for a theory of everything. String theory attempts to describe the fundamental constituents of the universe not as point-like particles, but as tiny, vibrating strings. In certain versions of string theory, the holographic principle naturally arises as a feature of the theory. In this framework, space and time themselves are emergent properties, woven together from more fundamental, lower-dimensional information. The implications of the holographic principle are profound and perplexing. If our universe is a projection from a lower-dimensional realm, it challenges our very understanding of what it means to exist in space and time. The objects we perceive as solid and real may be, at their core, an encoded representation on a distant cosmic boundary. But does this mean our everyday experiences are merely illusions? Not exactly. Much like a hologram provides a realistic representation of an object, the 3-dimensional world we navigate feels real because the encoded information is so richly detailed. The atoms that make up our bodies and the stars in the sky may be encoded on a cosmic boundary, but they still behave according to the laws of physics we observe in our familiar, everyday world. One of the most exciting aspects of the holographic principle is that it could provide a framework for resolving some of the biggest puzzles in physics. In particular, it offers a possible solution to the long-standing conflict between quantum mechanics, the theory that governs the very small, and general relativity, the theory that governs the very large. By viewing space-time itself as an emergent property from a more fundamental holographic description, the principle hints at a deeper unity between these 2 pillars of physics. While experimental confirmation of the holographic principle remains elusive, its theoretical foundation is robust, and physicists continue to explore its implications. For example, in 2017, researchers discovered hints of holographic duality in simple models of quantum entanglement, providing indirect support for the principle. Additionally, tools from holography have been used to study the behavior of quantum systems, giving rise to new insights into both condensed matter physics and the nature of gravity. In conclusion, the holographic principle stands as one of the most profound and speculative ideas in modern physics. It challenges our fundamental understanding of reality, suggesting that the universe we experience may be a projection from a lower dimensional boundary. While the idea remains largely theoretical, its potential to unlock deeper insights into the nature of space, time, and information continues to inspire physicists to push the boundaries of human knowledge. Whether or not the holographic principle turns out to be a true description of the universe, it offers a tantalizing glimpse into the depths of the unknown, reminding us that reality is often stranger than we can imagine. Quantum entanglement. Quantum entanglement is one of the most mysterious and fascinating phenomena in physics. It challenges our intuitive understanding of how the universe operates and has left some of the greatest minds, including Albert Einstein, puzzled. In simple terms, quantum entanglement occurs when 2 or more particles become so deeply connected that the state of one particle instantly influences the state of the other, no matter how far apart they are. This seemingly instantaneous communication defies the limits of relativity, which tells us that nothing can travel faster than the speed of light. To Einstein, this was spooky action at a distance. To understand how strange entanglement is, let's start with the basics of quantum mechanics. In the quantum world, particles like electrons or photons don't have definite positions or states until they are measured. Instead, they exist in a superposition of all possible states at once. When we measure a particle, it collapses into one specific state. Now, imagine we take two particles, let's say two electrons, and entangle them. In this entangled state, the two electrons are connected in such a way that measuring one will instantly determine the state of the other, even if they're light years apart. This isn't just a thought experiment. Entanglement has been demonstrated in many laboratory experiments and is a real phenomenon. To make this more tangible, let's use an analogy. Imagine you and a friend have a pair of gloves. You randomly take one glove, and your friend takes the other. You go to opposite sides of the planet without looking at your gloves. If you pull out your glove and see it's the left one, you instantly know that your friend has the right one, no matter how far away they are. That's somewhat like quantum entanglement, but with one critical difference. The gloves were always a left and a right glove. In the quantum world, before you look, both gloves could be left or both could be right. It's the act of looking that determines not only your glove's identity, but your friend's as well at the very same moment. But how does this instantaneous connection happen? Quantum mechanics doesn't offer a clear answer in terms of classical physics. What we do know is that the entangled particles are described by a single wave function, a mathematical object that encodes the probabilities of all possible states. When we measure one particle, this wave function collapses for both particles, ensuring that their states are correlated, but there's no signal traveling between them, at least not in the conventional sense. This brings us to why entanglement is so controversial and mind-bending. In Einstein's theory of relativity, information is limited by the speed of light. Nothing can travel faster than this universal speed limit. So the idea that entangled particles can influence each other instantaneously across vast distances seems to violate that rule. However, quantum mechanics doesn't involve any faster-than-light communication. Instead, it suggests that entangled particles are part of the same system, no matter how far apart they are. They don't need to communicate because they are not separate entities in the first place. Entanglement has been confirmed in numerous experiments, including the famous Bell test experiments, which have repeatedly shown that no local hidden variables, Einstein's proposed explanation, can account for the observed correlations between entangled particles. The implications of these results go beyond just abstract theory. Quantum entanglement plays a key role in quantum computing and quantum cryptography, two rapidly developing fields that could revolutionize technology. In quantum computing, entanglement is used to link qubits, the quantum equivalent of classical bits. Classical bits can be either 0 or 1, but qubits can exist in a superposition of both states at the same time. When qubits are entangled, the state of one qubit directly affects the state of another, no matter the distance between them. This entanglement allows quantum computers to perform many calculations simultaneously, making them exponentially more powerful than classical computers for certain tasks. Quantum cryptography, particularly quantum key distribution, QKD, uses entanglement to securely transmit information. In QKD, any attempt to eavesdrop on the transmission of information would disturb the entangled particles, making the intrusion detectable. This makes quantum cryptography theoretically immune to hacking based on conventional methods, offering unparalleled security. Entanglement also raises deep philosophical questions about the nature of reality. If entangled particles remain connected across vast distances, what does that say about the fabric of the universe? Some interpretations of quantum mechanics, like the many worlds interpretation, suggest that each measurement creates a branching of universes. Others propose that reality is fundamentally non-local, meaning that space and time may not be as absolute as we once thought. In conclusion, quantum entanglement is one of the most mind-expanding and counterintuitive aspects of quantum mechanics. It defies classical logic, challenges our notions of space and time, and has the potential to revolutionize technology. Whether through its role in future quantum computers or its philosophical implications about the connectedness of the universe, entanglement continues to be a profound mystery at the heart of modern physics. Wheeler's participatory universe. John Archibald Wheeler, one of the 20th century's most influential physicists, introduced a bold idea that redefined the relationship between the observer and the universe. Known as the participatory universe, this theory suggests that consciousness is not just a passive observer of reality, but an integral part of how the universe unfolds. In Wheeler's view, the act of observation doesn't just influence the outcome of quantum events. It helps create the very fabric of reality. This notion might seem like science fiction, but it's grounded in serious thought about the nature of quantum mechanics and the role of consciousness in shaping our understanding of the cosmos. Let's dive deep into Wheeler's participatory universe, using storytelling and analogies to make it accessible while maintaining its intellectual depth. To understand Wheeler's idea, we must first explore the observer effect in quantum mechanics. At the heart of quantum theory is a strange but well-documented phenomenon. Subatomic particles, like electrons or photons, behave differently when they are observed. Before an observation is made, these particles exist in a state of probability, a quantum superposition, where they are in multiple places or states at once. When someone measures or observes them, this superposition collapses into one definite outcome. A famous thought experiment that illustrates this is the double-slit experiment. When electrons are fired at a barrier with two slits, they behave like waves when not observed, creating an interference pattern on a detector screen, as if they passed through both slits at the same time. But when a detector is placed to observe which slit the electron goes through, the wave-like behavior disappears, and the electron behaves like a particle, passing through one slit only. This dramatic change in behavior based on observation suggests that reality at the quantum level is deeply tied to the presence of an observer. Wheeler took this idea one step further. He proposed that not only does the observer influence outcomes in the present, but the act of observation could potentially reach backward in time, influencing the past. Wheeler's delayed choice experiment is a thought experiment designed to challenge our classical ideas of time and causality. In this scenario, a photon is emitted and moves toward a barrier with two possible paths. A detector can either measure the photon as a wave or a particle after it has already traveled through one of the paths. What makes this experiment shocking is that the decision to observe the photon, and whether it behaves like a wave or particle, is made after it has already traveled through the barrier. In classical physics, this would seem impossible. How could a decision made in the present affect something that has already happened in the past? Yet, in Wheeler's model, this is exactly what happens. Reality, it seems, is not fixed until it is observed. The implication here is profound. The universe doesn't have a set history until someone looks at it. Wheeler suggested that this strange result points to something even more fundamental. Observation is not just a passive act. It's participatory, in a sense. We don't just observe the universe. We create it by interacting with it. Wheeler's participatory universe takes the observer effect to a cosmic scale. He believed that our observations are not limited to the micro-world of quantum particles, but extend to the universe as a whole. In his view, consciousness, the act of observing or measuring, plays an essential role in bringing reality into existence. Imagine the universe as a giant puzzle, but the pieces of the puzzle only exist when someone tries to fit them together. Wheeler's theory suggests that without observation, the universe remains in a state of potential, undefined, and incomplete. Only when conscious beings observe, measure, or interact with the universe does it take on the form we know. In this sense, Wheeler's universe is participatory. We are co-creators in the unfolding of reality. To illustrate this point, Wheeler coined the phrase "it from bit," suggesting that all physical things, emerge from bits of information, bit. In other words, the universe's structure is based on information, and observation is what brings this information into a physical state. Much like how a computer program remains dormant until a user interacts with it, the universe, according to Wheeler, remains in potential until an observer brings it into being. Wheeler's participatory universe implies that consciousness is not an incidental byproduct of the universe, but a fundamental component of it. This raises profound questions about the nature of life and mind. If observers create reality, then consciousness must have a special role in the cosmos. And since observation seems to be essential for the universe to take shape, the emergence of conscious beings like humans might not be a random accident, but an essential part of how the universe operates. Wheeler speculated that we might be part of a larger cosmic feedback loop, where the universe creates observers, and those observers, in turn, create the universe by observing it. This idea connects with the concept of the Anthropic principle, which suggests that the universe must be structured in such a way that it allows conscious life to emerge. Without observers, there would be no one to collapse the probabilities of quantum events into reality. Wheeler's participatory universe challenges us to reconsider what we know about reality and the role we play in it. Instead of a fixed, objective universe that exists independently of us, Wheeler proposed that the universe only fully exists when we interact with it. Observation becomes not just a tool for understanding the universe, but an essential act that brings it into being. Through the lens of this theory, we are not passive spectators in a universe that unfolds according to preordained laws. Instead, we are active participants, shaping the very fabric of reality through the act of observation and consciousness. In this view, the cosmos is not a distant, uncaring expanse of matter and energy, but something deeply intertwined with our existence. Wheeler's participatory universe is more than just a scientific hypothesis. It's a profound philosophical statement about the connection between mind and matter, observation and existence. If true, it places us at the heart of the cosmic process, suggesting that the universe is not just something we live in, but something we help create. Information theory of the universe. Imagine the universe as a vast, cosmic computer with everything from galaxies to subatomic particles functioning as data points. In this view, reality itself is underpinned not by matter or energy alone, but by information, the fundamental currency that dictates the behavior of everything that exists. This perspective, known as the information theory of the universe, suggests that the very fabric of the cosmos may be composed of bits of data, like the 1S and 0S that power our computers. It's a paradigm shift in how we understand reality, one that pushes us to rethink space, time, and matter in terms of information. To grasp the information theory of the universe, it's essential to first understand information theory as it was originally developed. In the 1940s, mathematician Claude Shannon devised a theory to quantify information, primarily to optimize communication systems. His work laid the foundation for the digital revolution by explaining how information could be stored, transmitted, and manipulated efficiently. In Shannon's theory, information isn't about meaning, it's about reducing uncertainty. The fewer possible outcomes an event has, the less information is needed to describe it. Applied to the universe, this theory suggests that at a fundamental level, everything is reducible to bits of data. Instead of understanding physical reality as solely composed of particles or waves, it can be understood as a giant information processing system. This leads to a radical view. The universe itself could be akin to a colossal computer, running a program that governs the behavior of everything from galaxies to electrons. One of the key concepts that brings information theory into cosmology is the black hole information paradox. According to classical physics, when something falls into a black hole, it disappears beyond the event horizon, the point from which nothing, not even light, can escape. In this process, all the information about the object, its composition, structure, and properties, appears to be lost forever. But quantum mechanics suggests that information can't simply vanish. It has to be conserved. This creates a paradox. How can information escape a black hole if nothing else can? The solution may lie in a profound understanding of information theory. Perhaps the information isn't lost, but encoded in the black hole's event horizon. Some physicists, like Stephen Hawking, propose that black holes could eventually emit this information through a process called Hawking radiation, allowing the information to be preserved. This realization deepened the connection between the universe and information. It suggested that even the most extreme environments in the cosmos, like black holes, adhere to the principle that information is never truly destroyed. The connection between black holes and information led to an even more radical idea, the holographic principle. This principle proposes that all the information contained within a three-dimensional volume of space can be encoded on a two-dimensional surface, much like a hologram. In other words, our three-dimensional universe could be a projection of information encoded on a distant two-dimensional boundary. In the context of information theory, this idea implies that the amount of information that can be stored in a region of space is proportional not to the volume of that space, but to its surface area. This counterintuitive insight is a cornerstone of modern theories about quantum gravity and the nature of space-time, linking the concept of information to the fundamental structure of the universe. Taking this a step further, some physicists, like Seth Lloyd, have proposed that the universe behaves like a quantum computer. A quantum computer operates using quantum bits, or qubits, which can exist in multiple states simultaneously. This allows for vast amounts of data processing far beyond the capabilities of classical computers. If the universe functions like a quantum computer, then its evolution over time could be understood as a complex computational process. Every interaction between particles, every force, and every physical law could be the result of information being processed and transformed. In this view, reality itself is a continuous computation, with the laws of physics acting as the software governing the cosmic hardware. This theory helps explain why the universe behaves in the highly ordered yet profoundly complex way that it does. It suggests that the universe's structure and evolution, from the formation of stars and galaxies to the interactions between subatomic particles, are driven by the processing of information. If the universe is fundamentally composed of information, then what we perceive as physical objects, rocks, trees, planets, are simply manifestations of underlying data. Just as a digital image on a screen is composed of pixels, reality may be composed of informational bits. This idea challenges the long-standing materialist view of the universe, suggesting that matter is not the most fundamental substance. Instead, it is information that underpins everything. Philosophically, this raises profound questions about the nature of existence. If information is the foundation of the universe, does this imply that reality itself is a kind of simulation or computation? Are we, as conscious beings, simply processing units within a grand cosmic computer? And if so, what is the purpose of this computation? These are questions that blur the line between physics and metaphysics, pushing us into uncharted territories of thought. The information theory of the universe offers exciting possibilities, but it also presents significant challenges. For one, it may help resolve some of the deepest mysteries in physics, such as the reconciliation of quantum mechanics with general relativity. Both quantum theory and Einstein's theory of gravity describe different aspects of reality, but they remain difficult to unite into a single framework. Information theory could serve as the missing link, providing a new way to understand the relationship between gravity, quantum mechanics, and space-time itself. Moreover, an informational universe has implications for our understanding of consciousness. If reality is fundamentally composed of information, then consciousness, our ability to perceive, process, and understand that reality, might be deeply connected to the informational structure of the universe. Could consciousness itself be a form of information processing? And if so, how does this fit into the broader computation of the cosmos? The information theory of the universe invites us to see reality in a new light, where everything, from stars to thoughts, can be understood as information. It suggests that the universe is not a cold, mechanical machine, but rather a dynamic, evolving system, driven by the processing of data. This perspective doesn't just change our understanding of the physical world, it alters our perception of ourselves and our place in the cosmos. In this grand computation, we are not mere spectators. We are participants, entangled in the flow of information that defines reality itself. Digital physics. Imagine for a moment that the universe, in all its complexity, behaves much like a computer simulation, a vast, intricate program made up of binary ones and zeros, where every atom, every star, and every quantum particle follows a predetermined set of instructions written into the very fabric of reality. This is the essence of digital physics, a provocative theory suggesting that the universe is not continuous, but is fundamentally discrete, operating much like the digital systems that power our computers. Digital physics proposes that at the most fundamental level, the universe may be akin to a vast computation, where everything from particles to physical laws is underpinned by digital information. This idea challenges traditional views of reality, which generally assume that space, time, and matter are continuous and can be divided into infinitely smaller parts. The central claim of digital physics is that space, time, and energy are not smooth and continuous, but are composed of indivisible units, small, discrete bits, much like pixels in a digital image. Just as you can't zoom in forever on a pixel without eventually seeing its individual blocks, the universe itself might have a smallest unit of space and time, beyond which further subdivision is impossible. These pixels of reality could be the Planck length for space and the Planck time for temporal intervals, extremely tiny scales where quantum effects dominate, and our classical understanding of physics begins to break down. Think of it this way. If you view the universe as an infinitely complex video game, everything in that game, from the player's character to the world around them, is ultimately reducible to code, strings of binary numbers processed by the game's underlying software. In the same way, digital physics suggests that the universe operates on fundamental code, and this code dictates how everything behaves at the smallest levels. The idea that the universe operates like a giant computation isn't new. One of the earliest proponents was Konrad Zuse, a German computer scientist who, in 1969, proposed that the entire cosmos could be understood as a computational system, where physical processes follow algorithmic rules, much like the functions of a computer. Later, physicist John Archibald Wheeler contributed a major philosophical leap to digital physics. His famous phrase, "it from bit," encapsulated the idea that every physical object, it, ultimately arises from informational bits. Wheeler proposed that at the quantum level, particles and forces may not exist independently but emerge from information. In this view, the fundamental building block of reality is not energy or matter, but information, just like in a computer. A central metaphor in digital physics is the concept of cellular automata. These are simple mathematical systems where a grid of cells follows specific rules to evolve over time. Despite their simplicity, cellular automata can generate incredibly complex patterns, almost like a simulation of life itself. These systems can represent much more than simple patterns. In fact, they are used in computer simulations to model everything from traffic flow to biological processes. Physicist Stephen Wolfram took this idea further, suggesting that the universe might operate as a kind of gigantic cellular automaton. In Wolfram's view, the entire cosmos could be generated by a simple set of rules, iterated over and over again at the smallest scales. Just as a computer game's world is built up from code, reality itself might be constructed from the evolution of binary or other discrete states following specific computational rules. Digital physics also intersects with quantum mechanics, where the universe's fundamental uncertainty seems to imply a link to information processing. Quantum bits, or qubits, represent quantum states that can be 0, 1, or both at the same time, a principle known as superposition. Quantum mechanics already suggests that reality, at its deepest level, doesn't conform to deterministic classical physics, but behaves more like a probabilistic computational process. In fact, quantum information theory has shown that quantum particles behave as if they process information. Entangled particles, for example, can communicate with each other instantaneously over vast distances, suggesting that some form of information transfer is happening in ways that defy classical physics. In digital physics, this can be likened to data transmission in a cosmic-scale computational system. Digital physics naturally leads to one of the most tantalizing and controversial ideas of all, the simulation hypothesis. According to this theory, the universe we perceive might be nothing more than an elaborate simulation, with reality itself being generated by some super-advanced computing system. If the universe is digital, and if all processes can be reduced to information and algorithms, then it becomes possible, in theory, that some advanced intelligence could run this universe, much like how we run simulations of virtual worlds in video games. Nick Bostrom, a philosopher at the University of Oxford, proposed the idea that if it's possible to create such a simulation, then it's highly probable that we are already living in one. After all, if future civilizations have the computational power to simulate conscious beings, it's possible that there are far more simulated realities than real ones. Thus, statistically speaking, it might be more likely that we live in a simulation than in the base reality. If digital physics holds true, it has profound implications for how we understand reality. It suggests that, at the most fundamental level, the universe might be structured by code and governed by informational processes. It challenges the classical view of a deterministic universe, and instead embraces a universe built from bits of data that evolve over time. Moreover, it raises questions about the nature of consciousness, life, and existence itself. If the universe is a computational system, Could consciousness itself be a form of computation? And if reality is ultimately digital, could we one day hack the universe, altering its code and changing the very laws of physics? Finally, digital physics forces us to reconsider our place in the cosmos. Are we mere players in a cosmic game, interacting with a reality that is essentially virtual? If the universe is a simulation, who or what created it? And what is the purpose of such a simulation? While digital physics is still speculative, it opens the door to fascinating possibilities that challenge our deepest assumptions about the nature of existence. Whether or not the universe is truly digital remains an open question, but the idea forces us to think of the cosmos as a complex system where information and computation play a fundamental role. By seeing the universe through this lens, we not only expand our understanding of reality, but also encounter profound questions about the nature of consciousness, life, and the fabric of the universe itself. Simulation theory is a provocative and mind-bending hypothesis, suggesting that reality as we know it may be an artificial simulation, much like a highly advanced video game or virtual environment. It postulates that everything we experience, our thoughts, emotions, sensations, even the laws of physics, could be generated by an immense computational system running in the background of what we perceive as reality. What makes this idea truly unsettling is that it isn't just a plot from science fiction. Serious philosophers, scientists, and technologists have contemplated whether we might already be living inside such a simulation. At the forefront of this discussion is philosopher Nick Bostrom, who in 2003 published a highly influential paper titled, "Are You Living in a Computer Simulation?" Bostrom's argument hinges on probability and logic, offering what is now known as the simulation argument. He presents three possibilities, only one of which he believes to be true. 1. Advanced civilizations will never develop the technological capability to run simulations of conscious being. 2. If such civilizations do exist, they will choose not to run simulations for moral or ethical reasons. Or 3. If both 1 and 2 are false, then the chances that we are living in a simulation are overwhelmingly high. According to Bostrom, if a civilization reaches a point where it can simulate entire realities, the number of simulated worlds could far outnumber the one real reality, implying that our existence is likely virtual. To better understand this, let's think of video games. In early games like Pong, the digital environment was incredibly simple, just 2 paddles and a ball. Today we have complex simulations in games like The Sims or Minecraft, where the environments are detailed and expansive. And characters within those games follow sets of rules that mimic the real world. But these worlds are just tiny simulations compared to what Bostrom imagines. A universe-scale simulation that could render every detail of our world in real time. If technology keeps progressing at its current pace, could there be a point in the future where a civilization develops computers powerful enough to simulate entire conscious worlds? One of the compelling reasons why simulation theory garners so much attention is that it offers an explanation for the unresolved mysteries of our universe. For instance, why does the universe seem to be governed by precise mathematical laws? In a simulation, the code would dictate the behavior of everything inside it, much like the rules of a video game. These laws, whether they describe gravity, electromagnetism, or quantum mechanics, could simply be part of the programmed framework, designed to create consistency within the simulation. This would explain why reality operates in a way that feels computational and formulaic. Another clue that might point toward us living in a simulation comes from quantum mechanics, specifically the idea of quantum indeterminacy. In quantum experiments, particles like electrons don't seem to exist in a defined state until they are observed, collapsing from a cloud of probabilities into a single measurable outcome. This behavior could be likened to how computer simulations manage resources. Objects and details aren't fully rendered until a player looks at them. If we're in a simulation, it might be computationally efficient for the system to only simulate certain aspects of reality when they're being observed or interacted with. A key question often raised about simulation theory is, why would an advanced civilization create such a simulation in the first place? The motivations could be varied. Perhaps they're studying their ancestors, us, by recreating historical conditions. Or maybe they're testing different outcomes in a virtual reality to predict or prepare for future events. It's also possible that the simulation is simply for entertainment or as a form of art for the beings running it. Reasons are speculative, but the fact that we can conceive of multiple motives only adds weight to the possibility. However, there are significant criticisms of simulation theory. One major point of contention is the assumption that it's even possible to simulate conscious being. While we've made great strides in AI and virtual environments, true consciousness, our experience of being, is still a profound mystery. Can consciousness be encoded in computer bits, or is it something unique to biological systems? Moreover, if we are in a simulation, how could we ever prove it? Any evidence we gather would be part of the simulation itself, and the creators could easily manipulate or hide any clues that might reveal the truth. But let's imagine for a moment that we could find proof. What would that mean for humanity? Would it diminish the significance of our lives, knowing that everything we experience is artificial? Or would it simply change our perspective, like discovering that we're part of a vast cosmic drama? Some argue that simulation theory, rather than being a source of despair, could offer new avenues for hope. If our universe is simulated, then perhaps we could learn to manipulate the simulation, breaking free from certain limitations of reality, maybe even achieving forms of digital immortality by integrating our consciousness into the simulation's framework. In the end, simulation theory offers a radical lens through which to view the universe, blending philosophy, technology, and metaphysics. It challenges our fundamental assumptions about reality, and invites us to explore questions that have fascinated humankind for millennia. What is the nature of existence? Is what we see truly real? And could the ultimate frontier of discovery lie not in space, but in the very fabric of reality itself? Whether or not we are indeed living in a simulated world, the theory itself expands the boundaries of thought and forces us to confront the mystery of our own consciousness. The many worlds. Interpretation. The many worlds interpretation, MWI, of quantum mechanics, is one of the most mind-expanding and radical ideas in modern physics. It suggests that every time a quantum event occurs, such as the decay of a radioactive particle, the path a photon takes, or the spin of an electron, the universe splits into multiple parallel versions of itself. In each of these universes, different outcomes of that quantum event play out. Rather than a single reality where only one outcome occurs, the many worlds interpretation posits that all possible outcomes actually happen, but in separate, coexisting worlds. To understand how MWI works, it's useful to begin with the problem it tries to solve, the famous paradox of quantum superposition. According to quantum mechanics, particles like electrons can exist in multiple states simultaneously. For example, an electron can be in a state of both spin up and spin down at the same time. This is called superposition. The puzzling part arises when we try to observe the particle. As soon as we make a measurement, the particle seems to collapse into one definite state, either spin up or spin down, but not both. Why does this collapse happen? And what causes the universe to choose one particular outcome over another? The traditional interpretation of quantum mechanics, known as the Copenhagen interpretation, claims that the act of measurement forces the system to collapse into one state, and this collapse is instantaneous and random. But this explanation is unsatisfying to many physicists. It introduces an element of randomness that feels arbitrary and doesn't explain what happens to the other possibilities, the ones that didn't occur in our universe. This is where the many worlds interpretation comes in, proposed by physicist Hugh Everett in 1957. Everett's idea was that the collapse never really happens. Instead, when a quantum event takes place, all possible outcomes occur, but in different branches of the universe. For instance, if you flip a quantum coin, it doesn't just land heads or tails. Both heads and tails happen, but in different universes. In one universe, you see heads, while in another, your counterpart sees tails. Imagine standing at a crossroads with two paths in front of you. In our everyday world, you can only choose one path. But in the quantum world of the many worlds interpretation, you take both paths, each in a different branch of the universe. From your perspective, you've made only one choice, but another version of you exists in the other universe, having made the opposite choice. The implications of this are staggering. If the many worlds interpretation is correct, then every quantum event, down to the smallest interactions at the atomic level, creates a branching of universes. This means there could be an almost infinite number of parallel realities, with every possible configuration of events playing out somewhere. In some universes, you might have chosen a different career or met different people. In others, entire galaxies might have formed differently, and the laws of nature might not even resemble those in our universe. One way to grasp the sheer scope of this idea is through Schrödinger's cat, a famous thought experiment in quantum mechanics. In the experiment, a cat is placed in a box with a quantum mechanism that has a 50% chance of killing the cat or keeping it alive. Until the box is opened, the cat is said to be in a superposition of both dead and alive. In the Copenhagen interpretation, when you open the box, the superposition collapses, and the cat is revealed to be either dead or alive. But according to the many worlds interpretation, there is no collapse. Instead, when you open the box, the universe splits into two. In one universe, the cat is dead, and in the other, it is alive. Both outcomes occur, but you, the observer, only experience one of them. Another version of you exists in the parallel universe, observing the opposite outcome. This may seem fantastical, but the many worlds interpretation has a certain elegance in its simplicity. It avoids the need for arbitrary collapse mechanisms or special observers who somehow cause quantum systems to choose one reality over another. Instead, MWI treats the entire universe, including observers, as part of the same quantum system, all governed by the same physical laws. In this view, the universe is constantly branching, creating an enormous multiverse of realities. Despite its radical nature, MWI is still a highly debated interpretation. Critics argue that it introduces too many unobservable realities, making it difficult to test or falsify. If these parallel universes are forever separated from our own, how can we ever know they exist? Additionally, some philosophers and physicists feel uneasy about the idea that every possible event happens somewhere, as it seems to strip meaning from choices and consequences. If every possible outcome occurs, does it matter what we do? However, supporters of the many worlds interpretation argue that it provides a natural solution to the mysteries of quantum mechanics, without introducing new, unexplained processes. From their perspective, the universe is already much stranger than we imagine, and MWI simply takes quantum mechanics to its logical conclusion. It also has intriguing implications for other fields, such as cosmology and black hole physics, where the concept of multiple realities could offer new insights into the structure of space and time. In the end, the many worlds interpretation pushes us to reconsider our understanding of reality. If every possible version of the universe exists somewhere, what does that mean for our sense of identity, free will, and existence itself? While we may never fully know if we inhabit one of countless parallel worlds, the exploration of these ideas stretches the boundaries of human imagination and forces us to confront the deepest mysteries of the cosmos. Take Marx's mathematical universe hypothesis, the mathematical universe. Hypothesis, proposed by physicist Max Tegmark, is a bold and thought-provoking theory that stretches the boundaries of how we understand reality. At its core, it suggests that the universe, at its deepest level, is not just described by mathematics, but is mathematics. In other words, everything we perceive, the galaxies, atoms, thoughts, and even ourselves, are fundamentally mathematical structures. This is not merely an observation that the universe follows mathematical laws, but a more radical claim. Reality itself is made of math. Let's explore this mind-bending hypothesis in detail, using analogies to clarify its most profound ideas. The first thing to understand about Tegmark's hypothesis is the deep connection between physics and mathematics. Since the dawn of science, mathematics has been the language through which we understand the universe. Newton's laws of motion, Einstein's equations of relativity, and Schrödinger's wave function all show that nature follows incredibly precise mathematical patterns. However, Tegmark takes this idea further. Rather than saying that math is just a tool we use to describe the universe, he argues that the universe itself is a mathematical structure. Think of it this way. If you look at a computer program, all of its operations boil down to a mathematical sequence, ones and zeros. The graphics, sounds, and interactions within the program are all manifestations of underlying mathematical algorithms. Tegmark's hypothesis posits that the physical world operates in a similar way. Just as the game or program emerges from code, the universe arises from its mathematical structure. Tegmark's mathematical universe hypothesis is closely tied to his broader view of the multiverse, which he divides into 4 levels. Each level represents a different kind of parallel universe, ranging from the familiar to the wildly abstract. Level 1, the cosmological multiverse. This is the most familiar concept of the multiverse, where there are regions of space beyond our observable universe. These regions might be too far away for us to ever observe, but they follow the same physical laws as our own universe. The key idea here is that due to the vastness of the cosmos, there could be regions where the initial conditions of the universe differ, creating universes that look different from ours. Level 2, the inflationary multiverse. In this version, different bubbles of space-time form in the aftermath of cosmic inflation, each with different physical constants. This means the laws of physics might vary from one bubble to the next, resulting in universes that are vastly different from our own. Some could have no stars, others could have entirely different particle physics. Level 3, the many worlds interpretation of quantum mechanics. This interpretation, which stems from quantum mechanics, suggests that every possible outcome of a quantum event actually happens in some branch of the universe. For example, when you flip a coin, the universe splits into two, one where the coin lands heads, and one where it lands tails. All possible outcomes exist, but in parallel realities. Level 4, a mathematical universe hypothesis. At this level, the most radical of all, every possible mathematical structure exists as its own universe. This means that universes aren't just bound by the physical laws we observe, but by any conceivable mathematical framework. These universes may operate, according to completely alien rules, incomprehensible to us, because their underlying mathematics is different. At the heart of Tegmark's hypothesis lies a provocative question. If the universe is mathematical, what does that say about existence itself? Tegmark suggests that everything, whether it's a rock, a cat, or a galaxy, can be understood as a set of mathematical relationships. The numbers and equations that describe the shape and motion of a planet are not just descriptions. They are the planet. Reality, in this sense, reduces to pure mathematics. To better grasp this idea, imagine that our universe is a gigantic complex equation. The objects within it, like stars and atoms, are just solutions to that equation. These solutions manifest as the physical entities and laws we observe, but underneath it's all math. According to Tegmark, our perception of space, time, and matter is simply the result of how these mathematical structures interact. A key philosophical question arises: why should the universe be fundamentally mathematical? Tegmark argues that mathematics has a kind of objective existence, just as the number 2 exists independently of any specific instance of two objects. Mathematical structures exist independently of whether they are realized physically. This is known as mathematical Platonism, the belief that abstract mathematical objects exist in their own right. For example, the equation x squared y squared 1 describes a perfect circle in two-dimensional space. That equation exists as a mathematical truth, regardless of whether any actual circles exist in the physical world. In Tegmark's view, the same applies to more complex mathematical structures that describe universes like ours. They exist out there in the same way that numbers and shapes do, and our universe is just one of many mathematical structures that happen to be realized. If Tegmark is correct, this hypothesis has profound implications for our understanding of reality and consciousness. Under the mathematical universe hypothesis, our sense of self, our thoughts, and even our perceptions of the physical world are simply emergent properties of a mathematical structure. Consciousness, in this view, is not something mysterious or supernatural, but arises from the arrangement and interaction of mathematical entities. This raises fascinating questions. Could other mathematical structures support entirely different forms of consciousness? Could universes with entirely different mathematical foundations host beings with thoughts and experiences utterly alien to us? Tegmark's hypothesis opens the door to an almost infinite variety of possible realities. Max Tegmark's mathematical universe hypothesis is a daring and radical idea that forces us to reconsider the nature of reality itself. If the universe is a mathematical structure, then everything we see, experience, and think is just a manifestation of math. While this idea might seem abstract, it offers a potential solution to one of the greatest mysteries of science: why the universe is so perfectly described by mathematics. In the end, Tegmark's hypothesis invites us to explore reality in a way that is both mind-expanding and humbling. If the universe is indeed a mathematical structure, then perhaps we are all part of a cosmic equation, playing out a mathematical dance that stretches across the multiverse, the Anthropic multiverse. In the vast theater of the cosmos, we find ourselves pondering a question that has both perplexed and fascinated humanity for centuries. Why are we here? What makes our universe uniquely suited for life? As we delve into the realms of cosmology and theoretical physics, one intriguing idea arises: the Anthropic principle. This principle suggests that the universe's fundamental parameters are finely tuned to allow for the emergence of conscious beings like ourselves. But what if this universe is merely one of many? Welcome to the concept of the Anthropic multiverse. Imagine standing at the edge of a serene lake. where the stillness of the water reflects the sky, seemingly capturing every nuance of light and color. Now envision that beneath this placid surface lies a vast network of interconnected lakes, each one harboring its own distinct ecosystem, physical laws, and life forms, or perhaps none at all. This image serves as a metaphor for our understanding of the universe. Just as each lake exists with its unique attributes, the multiverse proposes that our universe is just one of countless others, each governed by its own set of laws. The Anthropic principle, first articulated by physicist Brandon Carter in 1973, seeks to explain the apparent fine-tuning of the universe. It posits that the conditions we observe, such as the strength of gravity, the electromagnetic force, and the mass of elementary particles, are not just random happenstances. Rather, they are parameters specifically tailored to support life. If the universe were even slightly different, life as we know it might not exist. For instance, if the gravitational constant were altered by a fraction, stars might not have formed, leading to a cosmos devoid of the elements necessary for life. Yet if we consider the existence of multiple universes, each with its own physical constants and laws, the narrative shifts dramatically. Herein lies the essence of the anthropic multiverse. In this framework, our universe is not a unique anomaly, but rather one of an infinite collection of realities, each varying in its potential for life. If the multiverse theory holds true, the very reason we find ourselves in this life-supporting universe becomes clearer. We exist in this particular universe because it is one of the few that allows for conscious observers. Other universes might exist where conditions are far too hostile for life. But since we are here to ask these questions, we can only ponder the realms that are conducive to our existence. Imagine a cosmic lottery where each ticket corresponds to a different universe. Most tickets yield empty or inhospitable outcomes, but a select few produce winning combinations that allow for life. The universe we inhabit is one such winner, but the sheer multitude of other tickets in the cosmic draw ensures that life will arise somewhere, even if it's in a vastly different form or under completely alien conditions. The multiverse concept has gained traction among scientists and cosmologists, supported by various theories in physics, including string theory and quantum mechanics. In string theory, for example, the many different ways in which strings can vibrate give rise to different physical constants and forces, leading to a multitude of possible universes. Each vibrational state represents a unique universe, contributing to the expansive tapestry of the multiverse. However, the implications of the anthropic multiverse reach beyond mere theoretical constructs. They challenge our understanding of reality, existence, and our place within the cosmos. If our universe is just one of countless others, what does that mean for the meaning of life? Is our consciousness merely an accident in an indifferent multiverse, or does it serve a greater purpose within this vast array of existence? As we confront these existential questions, we are compelled to reconsider the nature of reality itself. As we explore the anthropic multiverse further, we will delve into the philosophical implications of this theory, examining how it reshapes our understanding of existence, destiny, and the human experience. Through the lens of this expansive framework, we can gain deeper insights into not only the cosmos, but also the very essence of what it means to be alive, in a universe teeming with potential, yet bound by the exquisite rarity of life. The stage is set for a journey through the infinite possibilities of existence, each universe a unique act, in the grand performance of the multiverse. Eternal inflation. Imagine blowing up a balloon, but instead of the balloon reaching a maximum size and stopping, it keeps expanding indefinitely. Even more intriguingly, imagine that as this balloon inflates, tiny bubbles form on its surface. Each of these bubbles begins inflating on its own, creating more bubbles, and those, too, keep inflating and generating their own bubbles. This vivid analogy offers a glimpse into one of the most fascinating and controversial ideas in modern cosmology: eternal inflation. Eternal inflation suggests that our universe is not a singular, isolated entity, but part of an infinite, self-perpetuating process that gives rise to countless bubble universes within a much larger multiverse. Each of these bubble universes, including our own, has its own unique properties and physical laws. The theory stems from an extension of the widely accepted inflationary model, which describes the rapid expansion of the early universe. To understand eternal inflation, we first need to explore the concept of inflation itself. Inflationary theory was introduced in the 1980s by physicist Alan Guth as a solution to several perplexing problems in cosmology. According to the standard Big Bang theory, the universe began as an incredibly hot, dense point and expanded outward. But this model left certain issues unresolved. such as why the universe appears so uniform and why space seems so flat. Inflation provided an elegant solution. The theory suggests that in the first tiny fraction of a second after the Big Bang, the universe underwent a period of extremely rapid expansion. During this period, space itself stretched at a rate far exceeding the speed of light, smoothing out any irregularities and making the universe appear uniform at large scales. This period of inflation ended, allowing the universe to cool and continue expanding at a slower rate, leading to the universe we observe today. While the original inflationary model explained many of the Big Bang's puzzles, it soon became clear that inflation might not stop everywhere at the same time. Instead, some parts of space could continue inflating while others slowed down, forming pockets of space where inflation ends, creating what we perceive as universes. This process can go on forever, generating new pocket universes endlessly, which leads to the concept of eternal inflation. In the simplest terms, eternal inflation suggests that the inflationary process is self-sustaining. While inflation ends in some regions of space, forming what we perceive as the universe, there are always other regions where inflation continues unabated. This creates a multiverse, a vast and potentially infinite collection of universes, each emerging from its own pocket of space where inflation has stopped. This notion of eternal inflation fundamentally changes our understanding of the cosmos. Rather than viewing our universe as a singular, all-encompassing entity, eternal inflation presents it as just one bubble in a sea of countless others, with each bubble potentially having its own set of physical laws and constants. In some of these bubbles, stars and galaxies may form, while in others, conditions could be so radically different that nothing familiar exists at all. At the heart of eternal inflation lies the interplay between quantum mechanics and general relativity. Inflation is driven by a scalar field, often referred to as the inflaton field. This field determines the energy driving the expansion of space. Quantum fluctuations in this field cause different regions of space to evolve in different ways. In some regions, the inflaton field decays, causing inflation to stop and a universe to form. In other regions, quantum fluctuations prevent the inflaton field from decaying, allowing inflation to continue indefinitely. This quantum randomness ensures that while inflation might end in our region, it continues in other regions, driving the creation of new universes. The process can be compared to a chain reaction. As one region of space stops inflating and forms a universe, other regions continue inflating, creating more universes and so on. In this way, inflation never truly stops. It becomes eternal. The concept of eternal inflation has profound implications for our understanding of reality. One of the most mind-bending ideas that emerges from this theory is the multiverse. If eternal inflation is true, then our universe is just one of many, perhaps an infinite number, each with its own distinct properties and physical laws. In some universes, the conditions may be radically different from our own, with completely different particles, forces, and dimensions. In others, the laws of physics may be similar, but with subtle variations. This leads to the possibility that somewhere in another universe, a version of you exists. But in a world where gravity is stronger, or the speed of light is different, or where the universe itself operates under entirely different principles. While this idea may sound like science fiction, it is a natural consequence of eternal inflation. Another implication of eternal inflation is the question of whether we can ever observe or interact with these other universes. While our universe is expanding, the space between us and other bubble universes is also expanding, at a rate so fast that these other universes may be forever out of reach. Even though we might never observe these other universes directly, their existence can have indirect effects on our understanding of the cosmos, especially when it comes to explaining certain features of our universe. While eternal inflation is an intriguing theory, it is not without its critics. One major challenge is the lack of direct observational evidence. Since other bubble universes are beyond our cosmic horizon and are likely forever unreachable, the multiverse aspect of eternal inflation remains speculative. Critics also point out that the theory raises more questions than it answers, particularly when it comes to explaining why our universe has the specific properties it does. Another criticism comes from the philosophical implications of eternal inflation. If there are an infinite number of universes, does that mean anything that can happen will happen? Does it mean that every possible version of reality exists somewhere in the multiverse? These questions push the boundaries of science into the realm of metaphysics and challenge our understanding of probability and causality. Eternal inflation paints a picture of the universe as an endlessly unfolding process where creation is ongoing and the cosmos is far larger and stranger than we can imagine. Whether or not eternal inflation turns out to be true, it provides a framework for thinking about the universe in radically different ways. It challenges our assumptions about beginnings and endings, showing us that the cosmos may be a place of perpetual creation, where new worlds are constantly being born. The Big Bounce theory. Imagine standing at the edge of time, looking out at the history of the universe. In most conventional models, this story starts with the Big Bang, a single point in time when everything we know, every particle, atom, and galaxy, burst into existence. But what if that wasn't the beginning at all? What if instead of a singular creation event, the universe has been continually expanding and contracting in a never-ending cycle, forever reborn after each collapse? This idea forms the core of the Big Bounce theory. The Big Bounce is an alternative to the traditional Big Bang model. According to this theory, the universe didn't begin with a single event, but has been going through cycles of expansion and contraction for an infinite amount of time. In each cycle, the universe expands from a compressed state, eventually reaching a maximum size before collapsing back in on itself, only to bounce back and begin expanding again. Instead of the universe starting from nothing and expanding indefinitely, the Big Bounce proposes that the universe has no true beginning or end, only transitions between different states of contraction and expansion. To fully understand the appeal of the Big Bounce, it helps to examine the issues surrounding the Big Bang and the notion of a singularity in the standard Big Bang theory. The universe starts from a singularity, a point of infinite density and temperature, where all the laws of physics as we know them break down. The singularity is a problem because it doesn't offer a meaningful way to describe the physical universe at that moment. Our understanding of time, space, and matter cease to function in this realm, leaving us without the tools to explain what happened at the very beginning. Physicists have long struggled with this concept. The singularity is an uncomfortable solution because it leaves many unanswered questions. Why did the universe expand from this state? What caused the initial singularity? Why did the Big Bang happen in the first place? Big Bounce theory offers a potential solution to these problems by avoiding the singularity altogether. In the Big Bounce model, the universe doesn't emerge from a singularity. Instead, it comes from the collapse of a previous universe. As the universe contracts, the laws of physics and the energy of the cosmos begin to shift. Just before the universe collapses entirely, some mechanism, such as quantum effects or modifications in the geometry of space-time, causes a rebound. The universe bounces back from this near collapse and begins expanding again, just as it did after the Big Bang. Each cycle is like a breath. The universe inhales as it contracts, reaching a point of maximum compression, and then exhales as it expands outward again. This process is not a one-time event, but rather an ongoing rhythm of the cosmos, stretching back infinitely into the past and potentially into the future. One of the key challenges of the Big Bounce theory is explaining what triggers the bounce. In classical general relativity, when a universe collapses, it should collapse all the way into a singularity. However, proponents of the Big Bounce argue that quantum gravity, a theory that combines the principles of quantum mechanics with Einstein's theory of general relativity, may prevent this from happening. Loop quantum gravity, LQG, is one possible framework that supports the Big Bounce. LQG suggests that space and time are not continuous, but are made up of tiny, discrete loops. At extremely small scales, the universe's space-time becomes quantized, preventing the singularity from forming. As the universe reaches an incredibly compressed state, quantum effects kick in, preventing it from collapsing entirely and causing it to bounce back instead. This quantum correction offers a way to sidestep the problem of singularity. In this view, the bounce happens because the fundamental fabric of space-time has a kind of built-in resilience. It can't be compressed beyond a certain point. And as the universe approaches this limit, it triggers the expansion phase. While the Big Bounce is a compelling idea, it's still a speculative theory, and physicists are actively searching for evidence to support it. One possible line of evidence comes from studying the cosmic microwave background, CMB, the faint radiation left over from the early universe. If the universe has undergone multiple bounces, there could be subtle imprints left in the CMB that hint at previous cycles. Another avenue for testing the theory lies in gravitational waves, ripples in the fabric of space-time, caused by massive cosmic events. Some researchers believe that gravitational waves from previous cycles could be detected, offering clues about the pre-Big Bang universe. However, it's important to note that direct evidence for the Big Bounce remains elusive. and the theory still faces significant challenges in explaining certain aspects of the universe's behavior, particularly in reconciling it with dark energy and the accelerated expansion of the cosmos. The Big Bounce also carries profound philosophical implications. If the universe is cyclical, it challenges the notion of a linear beginning and end to the cosmos. There is no creation event in the traditional sense, no moment when the universe first came into existence. Instead, existence is eternal, with each cycle of expansion and contraction continuing endlessly. This idea can be deeply unsettling or comforting depending on your perspective. For some, the notion of an infinite cyclical universe is a source of awe, a testament to the boundless nature of reality. For others, it raises existential questions. If the universe has no ultimate purpose or end point, what does that mean for our place in it? The Big Bounce theory offers a fascinating alternative to the traditional Big Bang model. By proposing that the universe has no singular beginning but instead moves through cycles of collapse and rebirth, it avoids some of the conceptual problems associated with a singularity. While the theory is still in its early stages and faces many challenges, it opens up new ways of thinking about the cosmos and our place within it. In the end, the Big Bounce suggests that the universe, like a great cosmic breath, might have no true origin or conclusion, only an eternal dance between expansion and contraction, creation and destruction, Ekpyrotic universe. Imagine the universe as a vast stage, but instead of a singular Big Bang that sparked everything into existence, what if the creation of the cosmos was the result of a collision? Not a collision of particles, but of massive, multidimensional objects known as brains. This is the central idea behind the Ekpyrotic universe theory, an alternative to the Big Bang model that proposes that our universe was born out of the collision of these higher dimensional brains. The Ekpyrotic universe, a theory that emerged in the late 1990s, is based on concepts from string theory and M theory, which suggest that the universe exists not just within the three spatial dimensions we observe, but within a larger, more complex framework of multiple dimensions. In this model, brownies are like vast, flat sheets that can move and interact in a higher dimensional space. The word Ekpyrotic comes from the Greek term for conflagration, or out of fire, evoking ancient myths where the cosmos is created from a catastrophic fiery event. In the Ekpyrotic model, the universe wasn't born from an explosive singularity, but from the collision of these brains, which set the stage for the formation of matter, energy, and time. In the standard Big Bang theory, the universe begins with a singularity, a point of infinite density and temperature where the laws of physics break down. After the singularity, the universe expands, cooling down as it grows, eventually leading to the formation of stars, galaxies, and all the structures we observe today. However, this model leaves many unanswered questions about the nature of the singularity itself, as well as what might have existed before the Big Bang. The Ekpyrotic model takes a different approach. According to this theory, two brains exist in a higher dimensional space, slowly moving towards each other over time. These brains may represent different parallel universes or different regions within a larger multiverse framework. As they approach one another, they create tension, similar to the buildup of energy before two tectonic plates collide in an earthquake. At the moment of collision, the energy released from the interaction between the brains causes the universe to begin expanding. This is what we perceive as the Big Bang. But instead of a singularity emerging from nothing, the universe's expansion is a product of this cosmic collision. One of the fascinating aspects of the Ekpyrotic universe is its link to M theory, a framework that extends string theory. In M theory, the universe isn't limited to the familiar three dimensions of space and one of time. Instead, there may be multiple spatial dimensions that we can't directly observe. Brownies, in this context, are objects that exist within these higher dimensional spaces. They can be incredibly large, stretching across vast scales, or small and localized. The Ekpyrotic model suggests that our universe is a three-dimensional brain that exists within a higher dimensional space. Other brains may exist parallel to ours, and these could be other universes with different properties and physical laws. The collision between two of these brains is what triggered the birth of our universe. This idea introduces a radical rethinking of cosmology. Our universe is just one slice of a much larger multiverse, and what we perceive as the birth of our cosmos is merely the result of interactions within this larger, higher dimensional reality. One of the most appealing aspects of the Ekpyrotic universe model is that it avoids the problem of the singularity. In the standard Big Bang theory, The singularity represents a breakdown in our understanding of the universe's earliest moments. The infinite density, temperature, and curvature make it impossible for current physical theories to describe what happens at this point. The Ekpyrotic model circumvents this issue entirely. Instead of beginning with a singularity, the universe's initial conditions are shaped by the slow approach and eventual collision of two brains. This offers a smoother transition from whatever existed before the universe began expanding. The brains gradually approach each other over potentially trillions of years, with the universe's beginning marked not by a catastrophic singularity, but by a gentle, albeit energetic, collision. One of the most fascinating implications of the Ekpyrotic universe is that the collision that gave birth to our universe might not be a one-time event. Just as the Big Bounce theory proposes an infinite cycle of expansion and contraction, the Ekpyrotic model suggests that the universe could go through repeated cycles of brain collision. After each collision, the universe expands and evolves as we know it, but over vast stretches of time, it begins to contract again. The brains move closer together once more, eventually leading to another collision, which in turn sparks the birth of a new universe. This cyclical process could have been happening eternally, with no true beginning or end, much like a cosmic heartbeat. While the Ekpyrotic universe shares similarities with the Big Bounce theory, both involve cyclic processes of universe creation and destruction. The key difference lies in how these events occur. In the Big Bounce model, the universe itself expands and contracts within a single framework of space and time. In contrast, the Ekpyrotic model involves the interaction of different brains within a higher dimensional space. The driving force behind each new cycle isn't just the contraction of a single universe, but the movement and collision of brains in higher dimensions. This makes the Ekpyrotic model both more complex and more connected to the cutting-edge ideas in string theory and M-theory. The Ekpyrotic universe challenges traditional views of the cosmos and our place within it. If the universe is part of a larger multiverse where brains collide to create new universes, then the scope of reality is far grander than we can comprehend. It raises profound questions. Is our universe unique? Or are there other brains that host entirely different kinds of universes? Is this cyclical process eternal, with no true beginning or end? This model also invites reflection on the nature of creation and destruction. Rather than a singular moment of creation, the universe becomes part of a dynamic process that is constantly evolving, collapsing, and rebirthing itself in a much larger, higher dimensional context. The Ekpyrotic universe offers a bold reimagining of how our cosmos came into being. Instead of a singular explosion from a point of infinite density, the universe emerges from the slow, graceful approach of two cosmic brains, whose collision sparks the expansion we know as the Big Bang. This theory not only provides a potential solution to the troubling concept of the singularity, but also ties the fate of our universe to a larger, more complex multiverse. In this model, creation is not a one-time event, but part of a grand cyclical dance, where the universe is born, grows, and collapses, only to rise again from the next collision of brains. It's a vision of the cosmos that expands our understanding of reality, and invites us to contemplate the eternal rhythms that govern the birth and death of universes. White hole cosmology, a mirror of the Big Bang. Imagine a cosmic event so powerful that it propels matter outward in every direction, a torrent of energy erupting into the universe. This image likely calls to mind the Big Bang, a widely accepted theory of how our universe began. But what if there existed a cosmic phenomenon that acts in reverse, spewing matter and energy out from an already formed universe rather than creating one from scratch? Enter the concept of the white hole. In the field of theoretical physics, a white hole is often described as the opposite of a black hole. While a black hole pulls everything into it, even light, allowing nothing to escape, a white hole does the exact reverse. It cannot be entered, but matter and energy can escape from it. White hole cosmology is an idea that takes this hypothetical phenomenon and applies it on a grand scale, envisioning a universe that might have been shaped, in part, by these mysterious forces. What is a white hole? To understand white holes, it's important to first grasp the concept of black holes. A black hole forms when a massive star collapses under its own gravity, becoming so dense that it creates a region where the gravitational pull is so strong that nothing, not even light, can escape. This boundary is called the event horizon. Once something crosses the event horizon, it is effectively lost to the universe, pulled inexorably into the black hole's singularity, a point of infinite density. Now, imagine time running backward from this scenario. If black holes consume matter, then white holes expel it. Where black holes represent regions of space-time where nothing can escape, white holes are regions from which nothing can enter, but things can emerge. In theory, a white hole could pour matter and energy out into the universe, much like a time-reversed black hole ejecting everything that had once fallen into it. White hole, cosmology, a new perspective on the universe. The concept of white holes was first proposed by the great minds of general relativity, specifically as solutions to the equations of Einstein's theory of general relativity. According to these equations, black holes and white holes could be viewed as two sides of the same coin. But while black holes have been widely accepted, white holes have remained a far more speculative idea. However, some cosmologists have explored how white holes could potentially explain certain features of the universe's evolution. White hole cosmology takes the idea of white holes and applies it to the universe at large. One radical suggestion is that the Big Bang itself may have been a white hole. In this view, the universe didn't just spring into existence from an unexplained singularity, but emerged as an outflow from a white hole-like structure. Just as matter and energy flow out of a white hole, the universe's initial expansion after the Big Bang could have been driven by such a cosmic event. The role of time and space. One of the most puzzling aspects of black and white holes lies in how they challenge our normal understanding of time and space. In a black hole, time effectively freezes at the event horizon for an outside observer. Inside the event horizon, space-time itself becomes so distorted that the usual laws of physics break down. In the case of white holes, the flow of time behaves in an equally strange but opposite manner. Instead of time freezing or pulling inward, time seems to push everything outward. In white hole cosmology, this reversal of time plays a crucial role. The expansion of the universe after the Big Bang could be viewed as a flow of time moving outward, causing space to expand and energy to spread throughout the cosmos. If white holes represent regions of space-time that expel matter and energy, then they might serve as models for understanding how time operates on a cosmic scale. Do white holes actually exist? Despite their intriguing nature, white holes remain purely theoretical. Unlike black holes, which have been observed indirectly through their gravitational effects on nearby stars and the bending of light around them, there is no direct evidence for white holes in the universe. White holes are not a feature of mainstream cosmology, but they do appear as a mathematical possibility within the framework of general relativity. Some theorists, however, argue that white holes might have existed in the early universe. They could have played a role in the formation of galaxies or the distribution of matter on a large scale. One speculative idea is that the universe's early rapid expansion, known as inflation, might have been driven by white hole-like mechanisms. After all, white holes would be expelling vast amounts of energy and matter, exactly the sort of thing needed to fuel inflation. Others have suggested that white holes could be linked to the mysterious dark matter that permeates the universe. Since dark matter does not emit light but exerts gravitational influence, some scientists have toyed with the idea that white holes could be responsible for these unseen gravitational effects. The link between black holes and white holes. Another fascinating possibility is that black holes and white holes could be connected. Some models of the universe suggest that when matter falls into a black hole, it doesn't simply disappear into the singularity. Instead, it could be expelled from a white hole in another part of the universe, or even in a different universe entirely. This is reminiscent of the science fiction idea of a wormhole, where black holes and white holes could be thought of as cosmic gateways between different parts of space-time. In this speculative view, black holes and white holes form a closed loop. Matter falls into a black hole and emerges from a white hole, continuing its journey through the universe in a never-ending cycle. While this idea remains speculative, it offers an intriguing possibility that links the two seemingly opposite phenomena. Conclusion: white holes and the mysteries of the cosmos. White hole cosmology remains a speculative but fascinating area of study. While there is no direct evidence for the existence of white holes, the concept challenges us to rethink the boundaries of time, space, and matter in the universe. Whether or not white holes are real, they offer a new perspective on the evolution of the universe and the forces that drive it. As we continue to explore the cosmos and deepen our understanding of black holes, gravity, and space-time, the mystery of white holes may one day offer us profound insights into the origins and future of the universe itself. Whether white holes played a role in shaping the cosmos or remain purely a mathematical curiosity, they represent one of the most mind-bending possibilities in modern physics. The no-boundary proposal, formulated by physicists Stephen Hawking and James Hartle in the early 1980s, is a radical idea that addresses the origin of the universe by eliminating the notion of a singular beginning. According to this proposal, the universe didn't have a singular, sharply defined moment of creation, such as the traditional Big Bang implies. Instead, it suggests a universe that has no boundaries in space and time, a theory that can be difficult to grasp, but becomes fascinating once its key elements are understood. To grasp the essence of the no-boundary proposal, imagine the concept of the Big Bang as commonly understood. In this model, the universe began from an infinitesimally small point, exploding outward to become the vast cosmos we observe today. This point, known as a singularity, is a moment when space, time, and matter all converge into a single point of infinite density. However, the singularity presents several problems. The laws of physics as we know them break down under such extreme conditions, making it impossible to predict or describe the nature of the universe at that instant. Furthermore, the question of what existed before the Big Bang becomes philosophically troubling. If time and space themselves emerged from the Big Bang, how can we conceptualize a before that doesn't include space or time? Hawking and Hartle's no-boundary proposal aims to resolve this dilemma by doing away with the need for a singular, definitive start to the universe. In this model, the universe can be compared to the surface of a sphere, like the surface of Earth. When walking on the surface of the Earth, there's no discernible edge or boundary where the surface simply ends. Instead, as you move forward, you might return to where you started after walking a full circle. Hawking and Hartle suggested that the universe could behave similarly in terms of time and space. It may have no clear-cut boundaries, but rather it could curve in on itself, avoiding a sharp beginning or end. In the no-boundary proposal, space and time are treated as interconnected dimensions, much like how Einstein's theory of general relativity treats them. This proposal modifies the Big Bang by blending time and space in such a way that, near the beginning of the universe, time itself becomes another dimension of space. In this framework, the universe doesn't emerge from a singular point of infinite density, but gradually smooths into existence, bypassing the need for a singularity, the imaginary time concept. A crucial aspect of the no-boundary proposal is the introduction of imaginary time, a concept that sounds more fantastical than it actually is. Imaginary time is not some kind of science fiction construct. It's a mathematical tool used in physics. Imaginary time helps to resolve issues that arise when trying to describe the universe at its earliest stages. In simple terms, imaginary time is another axis that physicists use in calculations, akin to the concept of complex numbers in mathematics. Just as complex numbers allow for more sophisticated calculations than real numbers alone, imaginary time allows physicists to circumvent the problems posed by singularities. In the no-boundary model, time, as we understand it, fades into this imaginary time near the beginning of the universe. In this phase, the universe becomes finite but unbounded, like the surface of a sphere. Thus, the need for an initial singularity, an impossible point where everything begins, is erased. Instead, the universe has a smooth, finite geometry that can be traced back through imaginary time, much like walking around a globe. One of the most significant implications of the no-boundary proposal is how it alters our view of creation. If the universe didn't have a singular beginning, but rather emerged smoothly from quantum fluctuations, as the proposal suggests, then the question of what caused the Big Bang becomes irrelevant. There is no abrupt transition from nothing to something, but instead a gradual process that creates space and time as part of the unfolding universe. In this sense, the no-boundary proposal leans into the idea that the universe might be self-contained, requiring no external cause or prior state to exist. It challenges traditional metaphysical ideas about a prime mover or first cause. Instead, the universe is a closed system, with no boundary conditions that need to be defined at the beginning, because there is no hard boundary or starting point at all. At its heart, the no-boundary proposal is a quantum theory of the universe's origins. In the quantum realm, particles don't behave deterministically, but rather probabilistically, existing in multiple states until they're observed. Similarly, this proposal suggests that the universe itself could have emerged from quantum fluctuations in a state of indeterminacy. Some extensions of the no-boundary idea even hint at the possibility of a multiverse. If quantum fluctuations can give rise to one universe, then theoretically they could give rise to many different universes, each with its own physical laws and configurations. Our universe might be just one of many, each created in a similar fashion, but with its own distinct features and rules. The no-boundary proposal is an elegant solution to the deep mysteries surrounding the origin of the universe, by eliminating the need for a singularity and suggesting that space and time might have curved into existence through quantum processes. It offers a new perspective on how the cosmos began. Though difficult to fully grasp, the idea of a universe without boundaries pushes us to rethink our understanding of time, space, and creation itself. This theory challenges both scientific and philosophical assumptions, opening up new questions about existence, the nature of time, and whether the universe truly needs a beginning at all. The block universe. Imagine you're standing on a street, observing the world around you. Cars are moving, people are walking, and time appears to flow naturally forward. The past is behind you, the present is here, and the future is yet to come. This is how we typically experience time, linearly, moment by moment. But what if time doesn't actually flow at all? What if every moment, past, present, and future, exists simultaneously, locked in place, like pages in a book? This is the idea behind the block universe, a philosophical and scientific concept that challenges our everyday understanding of time and existence. The block universe, also known as eternalism in philosophy, is a view of time that suggests all points in time are equally real. It's often compared to how we perceive space. Just as every point in space exists whether we're there or not, every point in time, past, present, or future, also exists, regardless of whether we're currently experiencing it. In this model, time is not something that flows or progresses. Instead, it is more like a four-dimensional block where every event, from the Big Bang to the distant future, is permanently set. The past is still there, the present is a specific slice of that block, and the future is already written, waiting to be experienced. To understand the block universe, we need to look at the concept of space-time, a term that combines space and time into a single four-dimensional structure. This concept was popularized by Albert Einstein's theory of relativity, which revolutionized our understanding of time. In relativity, space and time are not separate entities, but are intertwined in a fabric called space-time. Events in the universe occur at specific points in this fabric, and everything, light, planets, people, moves through it. Importantly, time is relative, meaning different observers can experience time at different rates depending on their speed and gravity. However, within the context of the block universe, every event, whether it's happening now or in the distant future, has a fixed location in space-time. An easy analogy would be a film strip. Every frame of a movie exists simultaneously on the strip, but we, the viewers, only see one frame at a time as it passes through the projector. The block universe suggests that time operates in a similar way. All frames of the universe exist at once, but we experience only one frame, the present, at any given moment. One of the most provocative implications of the block universe is that the passage of time is an illusion. We experience life as a series of moments strung together, with the past fading away and the future yet to come. But in a block universe, there is no moving forward in time. Every moment is static, existing eternally in its place. So why do we experience time as flowing? This question has puzzled physicists and philosophers alike. One explanation is rooted in how our brains process information. Our perception of time's flow might be an evolutionary adaptation, a useful way for us to interact with the world. But this perception doesn't necessarily reflect reality. It's like sitting in a train, watching the landscape go by. The trees and hills seem to be moving past us, but in truth, they're stationary. In the same way, time feels like it's moving, but according to the block universe, it's not. If every moment in time is already fixed, does that mean free will is an illusion as well? This is one of the most challenging philosophical questions raised by the block universe model. In this view, your future decisions are already there, waiting in the block of space-time, just as your past choices are set. But if the future is predetermined, how can you have free will? One way to resolve this is to distinguish between the feeling of free will and the actual structure of the universe. From within the block universe, you might still feel that you're making choices because you're only aware of the present moment, not the entirety of space-time. Your sense of decision-making is real within your experience, even if, from the perspective of the block universe, all your actions are part of the fixed structure of reality. Another perspective is that free will could exist within the context of the block universe, but only in a different way than we typically understand it. Instead of thinking of free will as creating the future, we might consider it as part of the structure of space-time. Your choices still define the shape of your life, but those choices are already built into the block. In other words, you are still the author of your actions, but those actions are part of a broader, fixed cosmic narrative. One of the key features of time as we experience it is its directionality, known as the arrow of time. We can remember the past, but we can't remember the future. Why? The arrow of time is closely tied to entropy, a concept from thermodynamics that measures disorder. Over time, entropy in the universe increases, meaning things become more disordered. For example, a shattered glass won't spontaneously reassemble, and heat flows from hot objects to cold ones, not the other way around. In the block universe, this increase in entropy still happens, but it's simply another feature of space-time. The past has lower entropy and the future has higher entropy, but both are equally real. Entropy gives time its direction from our perspective, but it doesn't contradict the block universe view where every moment, past or future, is part of a single, unchanging whole. The block universe presents a radical view of reality, one that challenges our deepest intuitions about time, free will, and existence. While it might be unsettling to imagine a universe where everything is already written in space-time, it also offers a kind of strange comfort. Just as every location in space exists regardless of where we are, every moment in time exists regardless of when we are. Whether or not the block universe is the ultimate truth, it forces us to rethink how we see time and reality. In a universe where every moment is equally real, the future isn't something we create, it's something we move through. We're passengers on a journey through a timeless, unchanging cosmos, where every choice we make and every event we experience is already part of the grand design. Time, dilation, and relativity. Time is a curious companion in our journey through life. It marches forward, indifferent to our desires, dreams, and despair. Yet what if I told you that time does not flow uniformly for everyone, that it can stretch, bend, and twist depending on speed and gravity? This is the remarkable reality of time dilation, a phenomenon that sits at the heart of Albert Einstein's theory of relativity. To grasp the concept of time dilation, let's embark on a thought experiment. Imagine two identical twin brothers, Alex and Sam. Alex remains on Earth, living his life in the familiar rhythm of days, months, and years. Sam, on the other hand, is an astronaut who travels at near light speed to a distant star. When he returns home after what he perceives as just a few years of travel, he discovers that decades have passed on Earth. This scenario illustrates time dilation in action, an intricate dance between speed, perception, and reality. Einstein's special theory of relativity, published in 1905, introduces us to the idea that time is not an absolute measure. Instead, it is intertwined with space in a four-dimensional fabric known as space-time. As objects move through this fabric, their velocity affects the passage of time. The closer an object travels to the speed of light, the more pronounced this effect becomes. In essence, time slows down for the moving object compared to a stationary observer. This is not merely theoretical. It has real-world implications that scientists have tested and confirmed with incredible precision. Consider a real-world application: GPS satellites. These satellites orbit Earth at high altitudes and speeds, where the effects of both special and general relativity come into play. Due to their velocity, time runs slightly slower for the satellites compared to clocks on Earth. At the same time, because they are farther from the Earth's gravitational field, time runs slightly faster for them as well. If engineers did not account for these relativistic effects, GPS systems would quickly become inaccurate, leading to navigational chaos. In this case, relativity isn't just a mind-bending concept. It's a practical necessity that keeps our global positioning systems functional. But time dilation isn't confined to extreme velocities. It also occurs in strong gravitational fields, as described by Einstein's general theory of relativity, introduced in 1915. Picture a massive planet or a black hole. The stronger the gravitational pull, the slower time flows relative to a weaker gravitational field. For instance, if you were to stand at the edge of a black hole while an observer remained far away, you would notice that time for you flows normally, but for your distant friend it appears to move much faster. This effect, often referred to as gravitational time dilation, highlights the profound connection between time and gravity. Let's visualize this concept further. Imagine you are on a trampoline, representing space-time, and you place a heavy bowling ball in the center. The fabric dips, creating a well around the bowling ball, akin to how a massive object distorts space-time. If you were to roll a marble around the bowling ball, it would spiral inward, drawn by the gravitational pull. To an observer watching from the sidelines, the marble's journey appears to slow down as it approaches the bowling ball, mirroring how time stretches in a gravitational field. This interplay of speed and gravity leads us to some intriguing philosophical questions. If time can be stretched and compressed, what does that mean for our perception of reality? Are we all experiencing time in the same way? When astronauts venture into space and return, they bring back stories of having traveled to the future, albeit in a manner that defies our intuitive understanding of time. Gravitational waves and the fabric of space. Imagine a tranquil pond, its surface reflecting the clear blue sky above. Now picture a stone thrown into that pond, creating ripples that expand outward, distorting the water's calm surface. This simple analogy captures the essence of gravitational waves, ripples in the fabric of space-time created by some of the universe's most violent and energetic events. Just as the stone disrupts the water, massive celestial bodies like colliding black holes or neutron stars disrupt the space-time around them, sending waves of energy across the universe. But what are these gravitational waves, and how do they reveal the hidden complexities of our cosmos? The concept of gravitational waves was first predicted by Albert Einstein in 1916 as part of his general theory of relativity. Einstein proposed that massive objects warp the fabric of space-time, and when these objects accelerate, they generate ripples in space-time, gravitational waves, that travel outward at the speed of light. However, for decades, this groundbreaking idea remained theoretical, waiting for technology to catch up with Einstein's vision. It wasn't until September 14, 2015, that the first direct detection of gravitational waves was confirmed by the LIGO, Laser Interferometer Gravitational Wave Observatory. The source? A cataclysmic collision between two black holes located about 1.3 billion light-years away. The detection was a monumental milestone in physics, confirming a century-old prediction and opening a new era in astrophysics. For the first time, we could hear the universe in a way that transcends light. To understand gravitational waves, we need to delve a bit deeper into the nature of space-time itself. Imagine space-time as a two-dimensional sheet of rubber stretched tight. When a heavy object, like a bowling ball, is placed on this sheet, it creates a depression, warping the surface. This is akin to how massive objects, such as stars or planets, curve space-time around them. When these massive bodies move, especially during dramatic events like collisions, they create ripples in space-time that propagate outward. These ripples alter the distances between objects in a very subtle way. In fact, LIGO measures these changes with incredible precision, detecting shifts in distance that are smaller than the diameter of a proton. This ability to measure minuscule changes in space-time is what allows us to listen to gravitational waves. Gravitational waves provide a novel way to observe the universe, complementing traditional electromagnetic observations, like those from telescopes that capture visible light, radio waves, or X-rays. This new perspective allows us to study astronomical events that were previously invisible to us. For instance, gravitational waves can reveal the presence of black holes, neutron stars, and even the dynamics of supernova explosions. One of the most remarkable aspects of gravitational wave astronomy is its potential to uncover the secrets of the universe's origins. By studying the waves emitted during the merging of black holes or neutron stars, scientists can glean information about their masses, spins, and distances. These insights can help refine our models of stellar evolution and the formation of compact objects, enriching our understanding of how the universe has evolved over billions of years. Beyond understanding existing cosmic phenomena, gravitational waves could also help us probe the very fabric of space-time itself. For instance, they may offer insights into the nature of dark matter and dark energy, two elusive components that make up most of the universe's content, yet remain largely unexplained. Furthermore, researchers are exploring how gravitational waves could illuminate events from the early universe, such as the Big Bang. Some theorists speculate that gravitational waves from this primordial era could still be lingering in the universe today, waiting to be detected. The quest to uncover these echoes from the past could redefine our understanding of the cosmos and its beginnings. As technology advances, the future of gravitational wave astronomy is incredibly promising. New observatories are being planned and constructed, including the Einstein Telescope and the Cosmic Explorer, which will be even more sensitive than LIGO. These new facilities will enable scientists to detect fainter and more distant events, vastly expanding our reach into the cosmos. Additionally, the intersection of gravitational wave astronomy with other fields, such as particle physics and cosmology, could lead to groundbreaking discoveries. By combining data from gravitational waves with electromagnetic observations and neutrino detections, researchers can create a multi-messenger framework to better understand complex cosmic events. Gravitational waves have opened a new window into the universe, allowing us to listen to its symphony. a melody composed of cosmic collisions, the births and deaths of stars, and the dance of massive celestial bodies. By studying these ripples in space-time, we can uncover the secrets of the universe, exploring realms that were once purely theoretical. Just as the ripples on a pond remind us of the impact of a single stone, gravitational waves remind us of the profound interconnectedness of the cosmos. Every collision, every merger, every moment of cosmic turmoil sends waves across the fabric of space, shaping the universe in ways we are only beginning to understand. As we tune in to this cosmic symphony, we embrace the thrill of discovery, piecing together the grand narrative of existence, one wave at a time. Non-Euclidean geometry. Imagine stepping into a vast, empty room where every surface is perfectly flat, and the angles between walls are all precisely 90 degrees. This room embodies the principles of Euclidean geometry, the familiar framework that has shaped our understanding of space since ancient times. In this Euclidean world, parallel lines never meet. The sum of the angles in a triangle is always 180 degrees, and the shortest distance between 2 points is a straight line. However, what if I told you that there are other ways to perceive geometry, ways that twist and turn the very fabric of space itself? Welcome to the world of non-Euclidean geometry, a groundbreaking field that reveals the complexities and curiosities of curved spaces. To fully grasp the significance of non-Euclidean geometry, it helps to first understand the principles of its Euclidean counterpart. In the realm of Euclidean geometry, we rely on a set of axioms laid out by Euclid over 2,000 years ago. One of the most famous of these is the parallel postulate, which states that for any given line and point not on that line, there is exactly one line parallel to the first that can be drawn through the point. This postulate gives rise to the flat, unbending world that has been foundational to mathematics and physics. However, mathematicians began to question the validity of this postulate. What if there are different geometries that exist beyond the limitations of Euclid's axiom? The pursuit of this question led to the development of non-Euclidean geometry, fundamentally altering our understanding of shapes, angles, and space. The story of non-Euclidean geometry begins in the 19th century when mathematicians like Carl Friedrich Gauss, Janos Bolyai, and Nikolai Lobachevsky independently explored alternative geometric frameworks. They proposed that if we modify the parallel postulate, we could discover entirely new types of spaces. Two main types of non-Euclidean geometry emerged from this exploration: hyperbolic geometry and elliptic geometry. 1. Hyperbolic geometry. In hyperbolic geometry, the parallel postulate is replaced with the idea that through a point not on a given line, there are infinitely many lines that can be drawn parallel to the original line. Picture a saddle or a Pringle chip. This surface curves outward in one direction while curving inward in another. In hyperbolic space, triangles can have angles that sum to less than 180 degrees. Imagine a triangle formed by 3 points on a hyperbolic surface. The corners of this triangle might stretch away from each other, creating more space than in Euclidean triangles. 2. Elliptic geometry. In contrast, elliptic geometry arises from the idea that there are no parallel lines. All lines eventually intersect, much like how lines of longitude on a globe converge at the poles. In this geometry, the sum of the angles in a triangle is greater than 180 degrees. Think of the surface of a sphere where the shortest distance between 2 points, known as geodesic, is along the curved surface, creating a wholly different spatial experience compared to flat geometry. Non-Euclidean geometry has profound implications, not only in mathematics, but also in our understanding of the universe itself. For centuries, mathematicians viewed Euclidean geometry as the only way to understand space. However, with the advent of non-Euclidean geometries, they discovered that the structure of space could be much more complex. One of the most fascinating applications of non-Euclidean geometry is in the field of relativity. Albert Einstein's theory of general relativity revolutionized our understanding of gravity, revealing that massive objects like planets and stars warp the fabric of space-time around them. This warping can be understood through the lens of non-Euclidean geometry. Instead of thinking of gravity as a force acting at a distance, we can conceptualize it as the curvature of space-time, where objects move along paths determined by this curvature. Consider the analogy of a stretched rubber sheet with a heavy bowling ball placed in the center. The sheet bends around the ball, creating a slope that causes smaller objects like marbles placed nearby to roll towards the bowling ball. This visual representation demonstrates how mass influences the curvature of space-time, illustrating the principles of non-Euclidean geometry in a tangible way. Beyond mathematics and physics, non-Euclidean geometry has also permeated art and philosophy. Artists like M.C. Escher played with non-Euclidean principles to create mind-bending visual illusions, where impossible shapes and perspectives challenge our perception of reality. These artworks invite viewers to question their assumptions about space and dimension, encouraging a deeper contemplation of the world around. Philosophically, non-Euclidean geometry forces us to confront the limits of human understanding. If the nature of space can be so profoundly different from our intuitive notions, what else might exist beyond the boundaries of our comprehension? It encourages an open-minded approach to exploration, pushing the boundaries of knowledge and imagination. The world of non-Euclidean geometry is a testament to the richness and complexity of mathematical thought. It challenges our long-held assumptions about space, revealing that there are many ways to perceive and understand the universe. Whether in the context of art, science, or philosophy, non-Euclidean geometry continues to inspire inquiry and creativity, reminding us that the universe is not simply a flat expanse, but a tapestry of intricate curved dimensions waiting to be explored. Through the lens of non-Euclidean geometry, we see that the fabric of reality may be far more complex and beautiful than we ever imagined. Quantum gravity. Imagine you're holding a grain of sand in your hand, a tiny object yet part of the vastness of the beach. Now zoom in closer, way closer, down to the atomic level where matter breaks into molecules, then atoms, and then even smaller particles like protons and electrons. Eventually you reach the realm of quantum mechanics, where the world behaves in ways that seem strange and alien compared to our everyday experience. But what if we zoom out again? This time, far beyond the beach, beyond the planet, to the scale of galaxies and black holes, where gravity dominates and space-time itself bends and warps. These two perspectives, quantum mechanics and general relativity, are the most successful theories in physics. Quantum mechanics governs the smallest scales, explaining the behavior of particles and the fundamental forces, except gravity. On the other hand, Einstein's theory of general relativity describes how gravity works on the large scale, showing that massive objects like planets and stars curve space-time, and it is this curvature that we perceive as gravity. Each theory works brilliantly in its respective domain, but when it comes to combining the two into a single framework, a theory of quantum gravity, we hit a wall. Quantum gravity is the attempt to reconcile these two seemingly incompatible theories, and it has proven to be one of the greatest unsolved puzzles in modern physics. It's like trying to merge two languages that have completely different grammars. One is probabilistic and deals with discrete particles, while the other is deterministic and continuous, describing smooth curves of space-time. To understand why merging them is such a challenge, let's first unpack what each theory tells us about reality. At the quantum level, reality is governed by uncertainty. Particles like electrons don't have definite locations until we observe them. Instead, they exist in a cloud of probabilities, where they could be in several places at once. Forces like electromagnetism are carried by particles called force carriers, such as photons. The theory of quantum field theory, QFT, extends this idea, treating particles as excitations in underlying fields that exist throughout space. These fields are what dictate the behavior of particles in the quantum world. However, gravity doesn't quite fit into this picture. According to general relativity, gravity isn't a force in the traditional sense. It's a feature of the fabric of space and time. Massive objects curve space-time, and this curvature tells other objects how to move. A planet orbits the sun, not because an invisible force is pulling on it, but because the sun's mass curves the space around it, and the planet follows that curved path. But in the quantum world, where particles move in discrete steps and fields are the fundamental building blocks, this smooth, continuous description of space-time becomes problematic. If we try to treat gravity like the other fundamental forces, such as electromagnetism or the strong nuclear force, we run into a paradox. When we zoom in on space-time to the smallest scales, called the Planck scale, the smooth fabric of space-time becomes grainy and erratic, like the foamy crest of a turbulent ocean wave. At these scales, general relativity breaks down, and we need a quantum theory of gravity to describe what's really happening. The search for quantum gravity is not just about solving an academic puzzle. It's essential for understanding some of the most extreme phenomena in the universe, such as black holes and the Big Bang. In these situations, the pull of gravity becomes so strong and the scales so small that both quantum mechanics and general relativity should apply simultaneously. But right now, we don't have a working theory that can handle both. One of the biggest challenges in creating a theory of quantum gravity is renormalization. In quantum field theory, when calculating interactions between particles, we sometimes get nonsensical infinite results. But physicists have developed techniques to cancel out these infinities, allowing us to get meaningful answers. When we try to apply these same techniques to gravity, though, the infinities don't cancel out. Gravity resists being tamed by the methods that work so well for other forces. There are several competing ideas for how to develop a theory of quantum gravity, with two of the most prominent being string theory and loop quantum gravity. String theory posits that instead of being point-like particles, the fundamental building blocks of reality are tiny vibrating strings. These strings can vibrate in different ways, and the different vibrational modes correspond to different particles. String theory also introduces extra dimensions beyond the familiar 3 of space and 1 of time. There could be as many as 11 dimensions, though they are hidden from view at the scales we typically observe. In string theory, gravity is explained by the existence of a particle called the graviton, which mediates the gravitational force. Theory provides a framework for unifying all fundamental forces, including gravity, under one mathematical roof. However, it remains speculative, as its predictions have yet to be experimentally verified. Loop quantum gravity, on the other hand, takes a more conservative approach. It suggests that space-time itself is not continuous, but is made up of tiny loops, woven together like a fabric. These loops are incredibly small, on the order of the Planck scale, and they form the fundamental building blocks of space-time. This theory avoids the infinities that plague attempts to quantize gravity using traditional methods, offering a possible path forward. However, loop quantum gravity, like string theory, is still incomplete and lacks direct experimental evidence. Understanding quantum gravity isn't just about solving a technical problem in physics. It's about unlocking a deeper understanding of the universe. The universe at its most fundamental level may not be what we perceive it to be. In fact, the very fabric of space and time might behave differently than we expect. Quantum gravity might reveal new insights into the nature of black holes, the beginning of the universe, and even the fundamental structure of reality. Just as quantum mechanics revolutionized our understanding of the microscopic world, and general relativity reshaped our view of the cosmos, the successful development of quantum gravity could be the key to the next great leap in physics, one that ties together all of reality's scales, from the tiniest particles to the largest galaxies, into a coherent picture. It's a quest to understand the deep interplay between the smallest building blocks of nature and the vast cosmic forces that govern the universe. Quantum loop gravity, QLG, or loop quantum gravity, LQG, is a theory that attempts to merge the two most successful frameworks of modern physics, quantum mechanics and general relativity. While quantum mechanics governs the behavior of subatomic particles with uncanny precision, general relativity explains the force of gravity and the large-scale structure of the cosmos. The issue is that these two theories, despite their immense success, don't naturally fit together. The challenge of combining them into a cohesive framework is one of the greatest quests in modern theoretical physics. Loop quantum gravity offers an alternative to string theory, another popular candidate for quantum gravity, and provides a unique approach to understanding how space-time itself might be quantized or broken down into discrete chunks of the smallest scale. To understand the motivation behind quantum loop gravity, let's first look at the mismatch between general relativity and quantum mechanics. General relativity describes gravity not as a force, but as the curvature of space-time itself, warped by the presence of mass and energy. Think of space-time as a flexible sheet, and objects like planets and stars as weights placed on it, creating dips and bends. This framework works exceptionally well for explaining large-scale structures like galaxies and black holes. On the other hand, quantum mechanics deals with particles and forces on extremely small scales, where uncertainty and probability rule. In quantum mechanics, forces such as electromagnetism are transmitted by particles like photons for light. If we try to apply these quantum principles to gravity, we run into serious issues. The smooth fabric of space-time described by general relativity clashes with the jittery, probabilistic world of quantum particles. The very idea of a smooth, continuous space-time breaks down at incredibly tiny distances, such as those near the Planck scale, a length of about 10 circumflex 35 meters, far smaller than any distance we can measure. Quantum loop gravity provides a novel solution to this problem. Instead of thinking of space-time as a continuous, unbroken fabric, LQG proposes that space-time itself is made up of tiny, discrete loops, much like how matter is composed of atoms. These loops are incredibly small, on the order of the Planck length, and they interweave to form a spin network, which is essentially the scaffolding of space. In this picture, space isn't a smooth sheet, but a network of interconnected loops, similar to a mesh or a grid. These loops represent the quantum states of space-time. Importantly, this means that space is quantized, just as matter and energy are quantized in quantum mechanics. There's no such thing as infinitely small space. Instead, space comes in finite, indivisible units. Time is also quantized in LQG, meaning that at extremely small scales, time doesn't flow smoothly but progresses in discrete jumps. This is a radical shift from our usual understanding of space and time, which seem to flow continuously in everyday experience. But at the quantum level, continuity breaks down. In LQG, the structure of space is described by what are called spin networks, which are mathematical graphs that represent the quantum state of space-time. Each edge of the graph corresponds to a quantum of space, and the nodes where edges meet represent regions of space with specific properties, such as volume. As the universe evolves, these spin networks change, with their structure shifting and reshaping over time. To visualize this, imagine a web of interconnected loops, the spin network, that continuously morphs and reshapes itself. There's an additional layer of complexity. These changes don't happen smoothly, but in discrete, quantized steps. When we consider not just space, but also the flow of time, this evolving spin network becomes what's called spin foam. Spin foam is the 4D version of the spin network, representing both space and time in a quantum universe. It's like a constantly shifting foaming structure where space and time emerge dynamically from these quantum interactions. One of the most exciting aspects of quantum loop gravity is how it eliminates singularities. The infinite densities and curvatures that arise in general relativity, such as those found at the center of black holes or at the Big Bang. In classical general relativity, when you try to trace the history of the universe back to its very beginning, you encounter a singularity, a point of infinite density where the laws of physics break down. However, in LQG, space-time is quantized, so it never reaches the infinite densities predicted by general relativity. The loops of space-time act as a natural buffer against such extremes, preventing the formation of singularity. For instance, instead of a singular Big Bang, the LQG predicts a big bounce, where the universe collapses to a minimum size and then expands again. This idea aligns with some modern cosmological theories that suggest the universe could undergo cycles of contraction and expansion. In LQG, geometry itself becomes a dynamic, evolving entity at the quantum level. This is one of the most profound consequences of the theory. Geometry is no longer a static backdrop in which events unfold, but is instead a fluctuating, interactive part of reality. The shape of space can change, twist, and evolve, and these changes affect the physical properties of the universe. At the smallest scales, geometry is defined by quantum states, and the familiar notions of distance and volume become probabilistic. The discrete nature of space-time also means that some familiar concepts, such as continuous motion or smooth geometry, no longer hold. Instead, objects jump from one location to another in a quantized fashion, just like how electrons jump between energy levels in atoms without passing through intermediate states. Quantum loop gravity offers a compelling vision of a universe where space and time themselves are woven from quantum threads. By breaking away from the idea of a smooth, continuous space-time, LQG attempts to solve some of the deepest problems in physics, including the clash between general relativity and quantum mechanics. While still in development, LQG is a bold step toward understanding the quantum nature of gravity and the fundamental structure of reality itself. This approach opens up exciting new possibilities for understanding black holes, the origins of the universe, and the ultimate fate of the cosmos. If correct, quantum loop gravity could reveal a universe that is far stranger and more interconnected than we ever imagined. Poincaré conjecture. Imagine standing on the edge of a vast, endless ocean, staring out at the horizon where the sea meets the sky. You notice the smooth surface of the water, perfectly reflecting world above. Now envision that this ocean represents the universe, vast and seemingly infinite, with every wave and ripple telling a story about the fabric of space itself. But what if, instead of a flat ocean, the surface had peculiar twists and turns, a shape that defied your intuition? Welcome to the world of topology and the fascinating journey of the Poincaré conjecture, a mathematical enigma that has intrigued mathematicians for over a century. Before diving into the conjecture itself, it's essential to grasp the concept of topology. Think of topology as a branch of mathematics that studies the properties of space that are preserved under continuous deformation, such as stretching, twisting, crumpling, and bending, without tearing or gluing. A common analogy is to imagine a donut and a coffee cup. In the eyes of a topologist, these two objects are equivalent because each has one hole. The donut has a hole in the middle, while the coffee cup has a handle. Through continuous transformations, one can morph from one shape to the other without any cuts. Topology focuses on what makes a shape fundamentally unique, rather than its precise measurements or angles. For example, a sphere and a cube are different topologically. No matter how you stretch or compress a cube, you cannot turn it into a sphere without altering its fundamental structure. Enter Henri Poincaré, a French mathematician, whose work laid the groundwork for modern topology in the early 20th century. In 1904, Poincaré posed a tantalizing question. If a three-dimensional shape is simply connected, meaning it has no holes, is it equivalent to a three-dimensional sphere? In other words, if you have a shape where any loop can be continuously shrunk down to a point without encountering any obstacles, can that shape always be transformed into a sphere? This seemingly straightforward question opened a Pandora's box of complexity. The conjecture was simple to state, but exceptionally challenging to prove, leading to years of research and exploration by mathematicians around the world. The Poincaré conjecture became a focal point of mathematical inquiry, inspiring countless attempts to either prove or disprove its validity. For nearly a century, the Poincaré conjecture eluded mathematicians. Some notable figures attempted to tackle it, employing various techniques and theories from different areas of mathematics, such as algebraic topology, differential geometry, and geometric topology. Each attempt brought new insights and deeper understanding, yet the conjecture remained unproven. The quest for a proof also highlighted the importance of dimensions in topology. While the conjecture specifically addressed three-dimensional shapes, mathematicians began exploring how it applied to higher dimensions. In four-dimensional space, for instance, the conjecture does not hold. It's possible to create shapes that are simply connected but not equivalent to a four-dimensional sphere. Then, in the early 21st century, a breakthrough occurred. In 2003, a Russian mathematician named Grigory Perelman published a series of papers that claimed to prove the Poincaré conjecture. His work built on the foundation laid by Richard S. Hamilton, who developed the theory of Ricci-Flow, a process that allows mathematicians to analyze the shape of a manifold over time. Perelman's proof was a remarkable achievement, using sophisticated geometric techniques to show that any simply connected three-dimensional manifold is homeomorphic to a three-dimensional sphere. In essence, he demonstrated that all the complex shapes in three-dimensional space could ultimately be transformed into a perfect sphere, adhering to Poincaré's original conjecture. Despite the elegance of his proof, Perelman's journey was not without challenges. After submitting his work, he faced skepticism and scrutiny from the mathematical community. Proving a conjecture as significant as Poincaré's required rigorous validation, and mathematicians spent several years meticulously reviewing his work. In 2006, it was finally confirmed that Perelman's proof was correct, earning him the prestigious Clay Millennium Prize, which included a $1 million reward for solving one of the 7 unsolved problems in mathematics. However, in a surprising turn of events, Perelman declined the prize, expressing dissatisfaction with the mathematical community and its values. His decision underscored the complex interplay between the pursuit of knowledge and personal recognition, leaving a lasting impression on the field of mathematics. The resolution of the Poincaré conjecture is monumental not only for its mathematical implication, but also for what it teaches us about the nature of space and shape. It provides a deeper understanding of how dimensions interact, and offers insights into the very structure of the universe. The proof has implications for various fields, including physics, computer science, and even biological systems. Furthermore, the journey of the Poincaré conjecture highlights the beauty of mathematics as an evolving discipline. It shows how a simple question can lead to a profound exploration of ideas that span generations. Poincaré's original conjecture continues to inspire mathematicians and lay people alike, serving as a testament to human curiosity and the relentless quest for knowledge. The Poincaré conjecture is more than a mathematical theorem. It is a narrative of exploration, perseverance, and discovery. From Poincaré's initial question to Perelman's groundbreaking proof, the conjecture exemplifies the intricacies of topology and the profound mysteries of the universe. It reminds us that the universe is not merely a collection of points and lines, but a rich tapestry of shapes and forms, waiting to be understood. Through the lens of the Poincaré conjecture, we see the power of human intellect in unraveling the complexities of the cosmos, pushing the boundaries of knowledge and understanding to reveal the underlying beauty of the mathematical universe. Zero-point energy. Imagine a vacuum, a space so empty that nothing exists within it. No particles, no matter, no light. In our everyday understanding, we might expect that such a void would be completely devoid of energy. However, quantum mechanics suggests something quite different. Even in the emptiest possible space, there is a vast, subtle energy quietly humming beneath the surface. This mysterious energy is known as zero-point energy, ZPE, and it has puzzled scientists for decades. Zero-point energy is the lowest possible energy that a quantum mechanical system can have. Unlike classical physics, which tells us that particles can be at rest and completely devoid of energy, quantum mechanics shows that even in a state of absolute rest, particles still possess a baseline amount of energy. This energy persists even at temperatures approaching absolute zero, where we would expect all motion to cease. The term zero point comes from the fact that this energy exists even at the ground state, at zero on the temperature scale. But it's crucial to understand that zero-point energy isn't something that we can see or measure directly in the traditional sense. It's the energy of the quantum vacuum itself, which is the foundation upon which the structure of the universe is built. To get a handle on zero-point energy, we first need to understand the nature of the quantum vacuum. Contrary to intuition, the vacuum of space is not truly empty. In quantum field theory, the vacuum is filled with fluctuating fields. These fields constantly produce and annihilate particle-antiparticle pairs, even in what appears to be empty space. Think of the quantum vacuum like the surface of the ocean. On a calm day, the ocean might look smooth, but beneath the surface, there are constant ripples and waves. The energy of these ripples, even when the ocean is at its calmest, is akin to zero-point energy. Even when a quantum system is in its lowest energy state, when all observable motion has stopped, there are still fluctuations of the quantum level. These fluctuations are an inherent part of the fabric of space itself. The idea of zero-point energy is rooted in one of the most fundamental concepts in quantum mechanics, Heisenberg's uncertainty principle. This principle tells us that we can never know both the position and momentum of a particle with absolute certainty. The more precisely we know one, the less precisely we can know the other. This uncertainty applies not just to particles but to energy as well. Because of this, it's impossible for a particle to ever have zero energy. If it did, we would know both its energy and its exact state, which would violate the uncertainty principle. As a result, even in a perfect vacuum, there is always some residual energy known as zero-point energy. One of the most compelling pieces of evidence for the existence of zero-point energy is the Casimir effect. In 1948, The Dutch physicist Hendrik Casimir predicted that if two uncharged parallel metal plates were placed close together in a vacuum, they would be pulled toward each other. This phenomenon occurs because the zero-point energy between the plates is different from the zero-point energy outside the plates. The result is a tiny but measurable force that pushes the plates together. The Casimir effect is one of the most direct demonstrations of zero-point energy at work. It shows that even in a seemingly empty space, quantum fluctuations create real physical effects. The idea that zero-point energy might be a vast, untapped energy source has captured the imagination of many scientists, engineers, and science fiction writers. If zero-point energy could be harnessed, it would represent a nearly infinite energy supply, an energy reservoir present throughout the universe that could power civilizations for millennia. But is this a realistic goal? While zero-point energy exists and exerts measurable forces, as in the Casimir effect, accessing and extracting this energy on a large scale is a different story. Quantum fluctuations are incredibly subtle, and the energy differences involved are minuscule. Most theoretical approaches to harnessing zero-point energy would require technologies far beyond our current capabilities. However, that hasn't stopped people from speculating. Some have suggested that zero-point energy could revolutionize space travel, providing a virtually limitless energy source for propulsion systems. Others have gone so far as to propose that certain unexplained phenomena, such as UFO sighting, could be the result of advanced civilizations utilizing zero-point energy. Implications of zero-point energy extend beyond just technological speculation. It plays a crucial role in various fields of physics, including cosmology and quantum field theory. For example, zero-point energy is related to the concept of dark energy, a mysterious force responsible for the accelerating expansion of the universe. Some physicists have speculated that dark energy might be a large-scale manifestation of the zero-point energy of the vacuum. Moreover, zero-point energy challenges our very understanding of reality. It suggests that even when we think we've stripped a system down to its most basic minimal state, there is still something more, an invisible, inexhaustible energy at the heart of existence. This raises profound philosophical questions about the nature of the universe. Is the vacuum truly nothing? Or is it the backdrop of an infinite quantum dance, teeming with unseen forces and energy? Zero-point energy is one of the most fascinating and mysterious concepts in modern physics. It defies our everyday understanding of emptiness and energy, suggesting that even the vacuum of space is alive with quantum fluctuations. While the dream of harnessing zero-point energy remains a long way off, its existence reshapes how we think about the universe and its underlying structure. As we continue to explore the quantum realm, we may uncover new ways to tap into this elusive energy source. But even if we never manage to harness it, zero-point energy will remain a testament to the richness and complexity of the quantum world, a reminder that even nothing is far more than it seems. The Broglie-Bohm theory. Imagine standing by the shore of a vast ocean, watching a boat glide smoothly across the water. The boat's movement is influenced by both its engine and the rippling waves beneath it, guiding its path. Now shift your focus from this familiar scene to the mysterious world of quantum mechanics. In this microscopic realm, particles like electrons move through space in ways that seem as unpredictable as a leaf floating in the wind. But what if, like the boat in the ocean, these particles are not as random as they seem? What if there is an underlying wave guiding them, a pilot wave? This is the crux of the de Broglie-Bohm theory, also known as the pilot waves theory, a fascinating yet often overlooked interpretation of quantum mechanics. Let's take a step back. Quantum mechanics, as it's commonly understood through the Copenhagen interpretation, tells us that particles exist in a strange superposition of states until they are observed. This idea is captured by the famous Schrödinger's cat thought experiment, where the cat is both alive and dead, until someone looks inside the box. The Copenhagen interpretation suggests that the act of measurement causes the wave function, a mathematical description of a quantum system, to collapse, determining the particle's position or state. But this interpretation has always been controversial, leaving many physicists uncomfortable with its inherent randomness and the idea that reality doesn't exist in a definite state until it's observed. Enter the Broglie-Bohm theorem, an alternative interpretation that seeks to restore a sense of determinism to quantum mechanics. Originally proposed by Louis de Broglie in 1927, and later expanded by physicist David Bohm in the 1950s, this theory posits that particles do indeed have well-defined positions and trajectories at all times, even when we're not looking. However, their motion is guided by an invisible pilot wave, a wave that encodes information about the particle's environment and helps steer its path. This is where the analogy of the boat on the ocean comes into play. Just as the boat's direction is influenced by the combination of its engine and the waves beneath it, in the de Broglie-Bohm theory, the particle's position is determined by the interaction between its own properties and the pilot wave. The particle is not floating aimlessly in a sea of probability, but instead is being guided along a specific trajectory, even if we can't always predict exactly where it is or where it will go. The beauty of the de Broglie-Bohm theory lies in its rejection of the wave function collapse. In this view, there is no mysterious process where reality snaps into place when observed. Instead, particles are always real, and their behavior is determined by a deeper, hidden layer of reality, one governed by the pilot wave. This notion is referred to as a hidden variable theory, because it suggests that certain variables, like the particle's precise position, exist but are hidden from our view due to the complexity of the quantum world. One of the most intriguing aspects of this theory is that it retains the key mathematical structures of quantum mechanics, including the famous Schrödinger equation, while providing a clearer, more intuitive picture of particle behavior. In experiments like the famous double-slit experiment, where particles are fired through two slits and create an interference pattern on a screen, the de Broglie-Bohm interpretation offers a unique explanation. While the particles themselves pass through one slit or the other, the pilot wave passes through both, creating an interference pattern that guides the particles to specific points on the screen. This elegantly accounts for the wave-particle duality of quantum objects without invoking the need for wave function collapse. Yet despite its explanatory power, the de Broglie-Bohm theory remains less popular than the Copenhagen interpretation. One reason is that it reintroduces a level of determinism to the quantum world, a concept that many physicists have become wary of. Additionally, the theory's reliance on hidden variables has been a source of debate, particularly after physicist John Bell's famous theorem in 1964, which shows that any hidden variable theory must be non-local, meaning that particles can instantaneously influence each other across vast distances. While this notion of non-locality might seem counterintuitive, it aligns with the well-documented phenomenon of quantum entanglement, where two particles remain connected even when separated by large distances. In essence, the de Broglie-Bohm theory invites us to reconsider our understanding of the quantum world. Instead of viewing particles as mere points of probability, it suggests that there is an underlying order, a hidden reality guiding the seemingly chaotic dance of quantum particles. This alternative interpretation doesn't just change how we think about particles, but it also reopens the door to a deterministic universe, where cause and effect are preserved, even in the quantum realm. Retrocausality. Imagine dropping a cup, and instead of it shattering on the ground, it somehow reassembles itself and leaps back into your hand. This scenario defies our everyday experience of the world, where cause leads to effect. The cup falls, and then it breaks. Yet, in the mysterious world of quantum physics, the idea of retrocausality challenges this fundamental view. Retrocausality is the notion that effects can precede their causes, that events in the present or future can influence outcomes in the past. It's an idea that feels both counterintuitive and revolutionary, flipping our understanding of time and causality on its head. Before diving deeper into retrocausality, it's important to understand the conventional view of time and causality. In classical physics, time flows in one direction, from past to future, like an arrow. This is often called the arrow of time, and it's evident in everything from thermodynamics, where heat flows from hot to cold, to the way we remember past events, but not future ones. In this framework, causes always precede their effects. You flip a light switch, the cause, and the light turns on, the effect. The idea of effects happening before their causes seems paradoxical, violating our intuitive grasp of reality. However, modern physics, particularly quantum mechanics, is not always beholden to our intuitive ideas of time and cause. In the quantum world, particles behave in ways that are so bizarre that they challenge the very foundations of how we understand reality. This is where retrocausality comes into play. Quantum mechanics deals with the behavior of particles on the smallest scales: atoms, electrons, and photons. One of the strangest aspects of quantum mechanics is its probabilistic nature. Particles don't have definite positions or properties until they are measured. They exist in a state of potentiality where they can be in multiple places or states at once, a phenomenon known as superposition. When we observe them, this wave of probabilities collapses into one reality. What's even stranger is the phenomenon of entanglement, where two particles, once linked, remain connected even across vast distances. If you measure the state of one particle, the other's state becomes determined instantly, no matter how far apart they are. This has led physicists to question the very fabric of space and time. How can information travel faster than the speed of light? Could it be that time itself doesn't behave the way we think it does? Retrocausality arises from this very line of question. If the outcome of a quantum event can be influenced by an observation made in the future, could it mean that time is not as rigid as we perceive? In other words, could future events determine past outcomes? A key experiment that brings retrocausality into sharp focus is the delayed choice experiment proposed by physicist John Wheeler. It's a variation of the famous double-slit experiment where a photon is fired at a barrier with two slits. If no measurement is made, the photon behaves like a wave, passing through both slits and creating an interference pattern on a screen. If a detector is placed to observe which slit the photon goes through, it behaves like a particle, passing through only one slit. In Wheeler's delayed choice version, the decision to observe the photon is made after the photon has already passed through the slits. Incredibly, the results suggest that the photon somehow knows whether it will be observed, and retroactively behaves like either a wave or a particle, even though the decision to measure is made after the photon's journey through the slit. This experiment raises mind-bending questions. How can a decision made in the present affect something that has already happened in the past? Wheeler's experiment seems to suggest that the act of observation in the present can retroactively determine the behavior of particles in the past, a form of retrocausality. Physicists are divided on how to interpret retrocausality. Some see it as an exotic yet plausible explanation for quantum phenomena, while others argue it could be an artifact of how we measure and understand the quantum system. Nonetheless, retrocausality offers an intriguing solution to some of quantum mechanics' deepest puzzles. One interpretation is that time itself might not flow in a straight line. Instead of being a one-way street, it could be more like a loop or a web, where events in the future and past are interconnected in ways that defy our traditional understanding of causality. In this view, what happens now could influence what happened yesterday, just as much as what happens yesterday influences today. Another possibility is that retrocausality could explain the non-local nature of quantum entanglement, where particles influence each other instantaneously across vast distances. Perhaps instead of information traveling faster than light, retrocausal influences could act backward in time, allowing entangled particles to remain connected through time itself, rather than space. While retrocausality is rooted in quantum mechanics, the implications of this idea extend far beyond the subatomic world. If time and causality can flow backward in the quantum realm, could there be effects on the macroscopic scale, the world we experience every day? This is one of the open questions that physicists are still grappling with. For now, there is no definitive evidence that retrocausality applies to everyday objects like coffee cups or cars. But the possibility that future events could influence the past remains a tantalizing idea, one that challenges the very foundation of cause and effect. It may also offer insights into unresolved mysteries in physics, such as the nature of time, the origins of the universe, and the enigma of consciousness. Retrocausality forces us to rethink the very fabric of reality. If time can flow backward, and the future can affect the past, then our understanding of cause and effect may need to be rewritten. Rather than time being a rigid, linear sequence of events, it could be more fluid and interconnected, with past and future dancing in a delicate balance. While retrocausality remains an area of intense debate and investigation, it offers a powerful reminder of how little we truly understand about the deep workings of the universe. As our understanding of quantum mechanics evolves, so too might our grasp of time itself. Perhaps in the grand cosmic scheme, time is less like an arrow and more like a spiral, one that curves and loops in ways we are only beginning to fathom. The bootstrap paradox. Imagine a time traveler stepping into a shimmering portal, leaving behind the familiar landscape of the present and plunging into the depths of the past. As they embark on this journey, they have a singular mission: to retrieve an artifact that holds monumental significance. But as they return to their own time, a perplexing question looms. Who originally created that artifact? Welcome to the bootstrap paradox, a mind-bending conundrum that challenges our understanding of time, causality, and the very fabric of reality. To grasp the intricacies of the bootstrap paradox, we must first visualize a scenario involving a famous piece of literature, a book containing the secrets of the universe. Picture a time traveler who travels back to the past, finds this book, and returns to the present with it. They then decide to publish the book, sharing its wisdom with the world. But here's the twist. When asked who wrote the book, the time traveler realizes there is no author. It has no origin. The traveler becomes both the reader and the author, caught in an infinite loop of cause and effect. This cycle raises profound questions. How can something exist without a definitive origin? What does this mean for our understanding of time? The bootstrap paradox is rooted in the concept of a closed causal loop, where an event or object exists without being created in the traditional sense. This idea prompts us to reconsider our intuitive understanding of cause and effect. In our everyday experiences, we perceive a linear flow of time. Past events lead to present circumstances which in turn shape the future. However, the bootstrap paradox disrupts this linear narrative, suggesting that time can fold back on itself, creating loops where effects precede their causes. Let's explore a more accessible analogy. Imagine you are a child with a favorite storybook that your grandmother read to you when you were young. Now, picture this scenario. One day you find the book in an antique store, but as you flip through its pages, you notice your name written inside, dated years before you even bought it. Intrigued, you ask your grandmother about it, only to learn that she has no memory of writing your name there. This puzzling encounter is akin to the bootstrap paradox, a story that seems to have no clear origin, yet exists within a tangled web of time. This paradox is not merely an abstract philosophical exercise. It has captivated the imaginations of authors, filmmakers, and scientists alike. The bootstrap paradox has found its way into popular culture, appearing in science fiction works such as Back to the Future and Doctor Who. In these stories, characters grapple with the complexities of time travel, often encountering situations that evoke the essence of the paradox. The allure of such narratives lies in their ability to stretch our minds and challenge our preconceptions about time. However, the implications of the bootstrap paradox extend far beyond the realm of fiction. They touch upon fundamental questions of existence and reality. If we consider the universe as a vast tapestry woven with intricate threads of causality, what happens when those threads intertwine in unexpected ways? Can we ever truly know the origins of our own experiences, thoughts, and creations if they exist within a closed loop? As we delve deeper into the bootstrap paradox, we must confront the philosophical ramifications it entails. The notion of free will, for instance, comes into play. If our choices are influenced by events that are, in essence, predetermined within a causal loop, do we retain agency over our actions? Are we simply players in a cosmic game where the rules are dictated by time itself? These questions force us to re-examine our understanding of autonomy and the nature of reality. Moreover, the bootstrap paradox invites us to reflect on the very structure of time. Is time linear as we often perceive it? Or could it be more akin to a complex web of interconnected events? The idea of time as a loop challenges our conventional notions and encourages us to think of existence as a dynamic interplay between cause and effect. a dance of possibilities rather than a rigid sequence of events. As we navigate through the intricacies of the bootstrap paradox, we are reminded of the delicate balance between imagination and reason. The allure of time travel and the mysteries it encompasses invite us to explore not only the mechanics of the universe, but also the very essence of our existence. With each twist and turn in the narrative, we discover that the paradox is not merely a theoretical construct. It is a reflection of our profound desire to understand the universe and our place within it. In this quest for understanding, the bootstrap paradox serves as a reminder that the exploration of time, causality, and consciousness is a journey without a definitive endpoint. It beckons us to continue questioning, dreaming, and seeking, even in the face of uncertainty, as we traverse the intricate pathways of time and existence. The paradox becomes a gateway into the uncharted territories of thought, where the boundaries of reality blur and the possibilities are as infinite as time itself. Quantum Zeno effect. Picture a movie theater filled with anticipation. The lights dim and the film begins to play. But just as the story starts to unfold, someone in the back repeatedly shouts, "Hold!" The film freezes, and viewers become trapped in a single moment, never able to experience the progression of the story. In a sense, this bizarre scenario mirrors the fascinating world of quantum mechanics and introduces us to the quantum Zeno effect, QZE, a phenomenon that suggests that frequent observation can actually influence the state of a quantum system. To appreciate the quantum Zeno effect, we first need to delve into the strange and counterintuitive realm of quantum mechanics. At its core, quantum mechanics describes the behavior of particles at the atomic and subatomic levels. Unlike our everyday experiences, where objects behave predictably, quantum particles can exist in multiple states at once, a concept known as superposition. Imagine flipping a coin. While it's in the air, it can be thought of as both heads and tails simultaneously, until you catch it and observe the outcome. In this quantum world, the act of measurement plays a pivotal role. When we observe a quantum system, we force it into a specific state, collapsing its wave function from the superposition of possibilities to a definite outcome. This peculiar behavior raises profound questions about the nature of reality and the role of observers in determining it. The quantum Zeno effect arises from this interaction between observation and quantum states. Named after the ancient Greek philosopher Zeno of Elea, known for his paradoxes about motion and change, the QZE suggests that if you measure a quantum system frequently enough, you can effectively freeze its evolution. In simpler terms, continuous observation can prevent a quantum system from transitioning to different states. To illustrate this concept, consider a simple analogy, a movie of a sprinter running a race. If you were to take snapshots of the runner at very short intervals, the series of still images would give the impression that the runner is barely moving at all. If you took fewer snapshots, however, the motion becomes apparent. In the quantum realm, if a particle's state is measured repeatedly within a short time frame, it remains in its initial state, effectively delaying its transition to a different state. The quantum Zeno effect is not merely a theoretical construct. It has been observed in various experiments. One notable experiment involved atoms transitioning between energy states. Researchers found that by continuously measuring the energy state of an atom, they could inhibit its transitions, demonstrating that observation could indeed influence its behavior. Another fascinating example of the QZE is found in the world of quantum bits, qubits, the building blocks of quantum computing. In quantum computers, qubits can exist in superpositions of states, allowing them to perform complex calculations much faster than classical bits. However, if qubits are frequently measured during computation, the quantum Zeno effect can cause them to remain in their original state, hindering the computational process. The implications of the quantum Zeno effect extend beyond mere curiosity. They raise profound questions about the nature of reality, observation, and the boundaries of human knowledge. The fact that observation can influence the behavior of quantum systems challenges our traditional understanding of physics and invites us to rethink the role of observers in the universe. The quantum Zeno effect also has potential applications in various fields, particularly in quantum computing and quantum information theory. Understanding how to manipulate quantum states through observation could lead to more efficient algorithms and error correction techniques. ultimately paving the way for more powerful quantum computers. The quantum Zeno effect invites philosophical contemplation about the nature of reality itself. If the act of observation can alter the behavior of quantum systems, what does this mean for our understanding of the universe? It raises questions about the relationship between consciousness and reality, whether the observer's awareness plays a fundamental role in shaping the world around them. Consider the implications of this effect in our daily life. How often do we pause to observe and analyze situations, potentially stunting their natural evolution? The quantum Zeno effect serves as a metaphor for the challenges of decision-making and the paradox of overthinking, reminding us that sometimes allowing events to unfold organically can lead to more authentic experiences. Quantum Zeno effect is a mesmerizing phenomenon that reveals the intricate dance between observation and quantum mechanics. Like the sprinter frozen in time by incessant snapshots, quantum system can be held in a particular state through the act of continuous measurement. This effect not only deepens our understanding of quantum behavior, but also provokes philosophical reflections on the nature of reality and the role of observer. As we navigate the complexities of the quantum world, the quantum Zeno effect serves as a reminder of the wonders and mysteries that lie at the intersection of observation and existence. It invites us to explore the delicate balance between knowing and not knowing, prompting us to reflect on our own interactions with the world around us. In this intricate tapestry of reality, observation is not merely passive, it is an active force that shapes the unfolding narrative of the universe. Tachyons and faster-than-light particles. Imagine a world where travel across vast distances occurs in the blink of an eye, where the stars are not distant points in the night sky, but reachable destinations within moments. This concept has captivated the imagination of humanity for centuries. From the tales of fantastical flying machines in ancient myths to the sleek starships of modern science fiction. At the heart of this pursuit lies a tantalizing idea. Tachyons, hypothetical particles that defy the conventional limits of speed and, in theory, can travel faster than light. To comprehend the implications of tachyons and their potential existence, we must first explore the foundations of modern physics and the nature of light. In the early 20th century, Albert Einstein revolutionized our understanding of the universe with his theories of special relativity. One of the central tenets of this theory is that the speed of light in a vacuum is the ultimate speed limit of the universe. According to Einstein, as an object approaches the speed of light, its mass effectively increases, requiring ever more energy to continue accelerating. This implies that reaching or exceeding the speed of light is impossible for any object with mass. The consequences of this theory have been profound, reshaping our notions of space, time, and the very fabric of reality. Einstein's insights led to a deeper understanding of time dilation, the phenomenon where time slows down for objects moving at relativistic speeds compared to those at rest. This has been confirmed by numerous experiments, including observing particles in particle accelerators and the precise synchronization of atomic clocks on fast-moving airplanes. However, the idea of traveling faster than light remains a tantalizing enigma, pushing the boundaries of our understanding. The concept of tachyon. Enter the concept of tachyon, theorized in the context of relativistic physics. The term tachyon is derived from the Greek word tachos, meaning swift or fast. These hypothetical particles possess an intriguing property. They would always travel faster than light, with a mass that becomes imaginary as their speed approaches the speed of light. This raises profound questions about causality, the principle that cause precedes effect, since faster-than-light travel could lead to scenarios where an effect occurs before it's caused, creating paradoxes that challenge our intuitive understanding of time and reality. To visualize this concept, imagine a race between two runners. The first runner starts at the starting line and races ahead, while the second runner, the tachyon, begins at the finish line and moves backward through time to reach the starting line before the first runner. This peculiar behavior introduces complexities that boggle the mind and complicate the very structure of space-time. If tachyons could exist, the implications for physics and our understanding of the universe would be revolutionary. For one, they might provide a mechanism for faster-than-light communication, potentially allowing information to be transmitted instantaneously across vast distances. This concept has tantalized scientists and science fiction enthusiasts alike, igniting discussions about the potential for interstellar communication and exploration. However, the existence of tachyons also raises significant challenges. If information could travel faster than light, it might lead to paradoxes that undermine the foundations of causality. For instance, imagine sending a message back in time using a tachyon. This could create a situation where the recipient acts on the information before it was even sent. Such scenarios complicate our understanding of cause and effect, challenging the coherence of our universe. Despite the tantalizing possibilities, tachyons remain purely hypothetical. To date, no experimental evidence has conclusively proven their existence. Researchers have explored various avenues to search for tachyons, including experiments in particle physics and theoretical investigations in string theory, where the concept of extra dimensions might allow for the existence of faster-than-light particles. One notable example involves high-energy particle collisions in accelerators like the Large Hadron Collider, LHC. Researchers hope to detect unexpected particles or behaviors that could hint at the presence of tachyons. Additionally, the study of cosmic rays, high-energy particles originating from outer space, has also sparked interest in the potential for faster-than-light phenomena. Tachyons have also found their way into popular culture, appearing in various science fiction narratives, from the warp drives of Star Trek to the tachyon beams in Doctor Who. These fictional representations capture the imagination and showcase humanity's enduring fascination with the idea of faster-than-light travel. While these stories may stretch the boundaries of scientific plausibility, they serve as a reflection of our longing for exploration and the mysteries that lie beyond our reach. The concept of tachyons and faster-than-light particles occupies a unique space in the intersection of theoretical physics and human imagination. While firmly rooted in the realm of speculation, tachyons challenge our understanding of the universe, prompting us to question the fundamental laws that govern reality. The exploration of these hypothetical particles pushes the boundaries of human knowledge and inspires curiosity about the nature of space, time, and existence itself. The brain as a quantum computer. Imagine for a moment standing at the edge of a vast, intricate forest. As you gaze into the dense thicket, you begin to see a network of paths winding in all directions, each leading to different destinations. This forest represents the human brain, a complex web of connections and pathways that guide our thoughts, decisions, and perceptions. Now imagine that this forest is not only vast, but also capable of existing in multiple states simultaneously, much like a quantum system. This brings us to an intriguing and controversial idea: the brain as a quantum computer. To understand the concept of the brain functioning like a quantum computer, we first need to touch upon the fundamentals of quantum mechanics. At its core, quantum mechanics is the study of the behavior of particles at the smallest scale: atoms, electrons, and photons. One of its most fascinating features is superposition, where a quantum particle can exist in multiple states at once. For instance, an electron can be in various positions until it is measured, at which point it collapses into a single state. Another crucial aspect of quantum mechanics is entanglement, a phenomenon where particles become interconnected such that the state of one particle instantly influences the state of another, regardless of the distance separating them. These principles challenge our classical understanding of reality and have led some researchers to ponder whether the human brain, with its complexity, could also utilize these quantum principles to process information. The human brain is composed of approximately 86 billion neurons, each forming thousands of connections called synapses. This immense network enables the brain to process vast amounts of information, much like a highly sophisticated computer. However, traditional models of computation do not fully account for the richness of human consciousness, creativity, and intuition. This is where the quantum brain hypothesis comes into play. Proponents of the quantum brain theory suggest that the brain's processing capabilities might not only rely on classical neural activities, but also engage in quantum phenomena. For example, certain biological processes within neurons, such as quantum tunneling, could theoretically allow for faster information processing and greater computational power. Imagine if instead of walking along a path through the forest, you could leap over barriers, or traverse multiple paths simultaneously. This metaphor captures the potential advantages of quantum computation. A central tenet of quantum computing is the concept of quantum coherence, where quantum states remain interconnected and maintain superposition, allowing for complex calculations. Researchers have found that certain biological systems, including the photosynthetic processes in plants and the magnetic orientation of birds, can exhibit quantum coherence. This raises the question, could the human brain similarly utilize quantum coherence to enhance its cognitive function? In the brain, molecules like microtubules, which are structural components within neurons, have been proposed as potential sites for quantum processing. These tiny structures could facilitate quantum coherence and superposition, enabling neurons to process information in ways that classical computing cannot. If this is indeed the case, it would suggest that our thoughts and decisions are influenced by quantum states, providing an explanation for phenomena such as intuition, creativity, and even déjà vu. If the brain operates as a quantum computer, the implications for our understanding of consciousness and intelligence are profound. It could suggest that human cognition is inherently more complex than traditional models allow. This idea aligns with the notion that consciousness is not merely a byproduct of neural activity, but rather a dynamic interplay of classical and quantum processing. Moreover, if the brain harnesses quantum computation, it could explain why our thoughts and perceptions often transcend logical reason. For example, we might experience sudden insights or solve problems in seemingly irrational ways. This quantum aspect of cognition may help illuminate the creative processes in art, music, and innovation, where leaps of understanding often appear disconnected from linear thinking. Despite the allure of the quantum brain hypothesis, it is essential to approach it with caution. Critics argue that the brain operates at a warm, wet temperature, which could disrupt delicate quantum states. Quantum coherence typically requires extreme conditions, such as those found in controlled laboratory environments. However, research in the field of quantum biology continues to explore whether certain quantum processes could withstand biological conditions. Additionally, while intriguing, the idea that the brain functions as a quantum computer remains largely speculative. Experimental evidence directly linking quantum phenomena to cognitive processes is still lacking. As researchers continue to investigate the complexities of the brain and quantum mechanics, the quantum brain hypothesis serves as a stimulating framework for exploring the nature of consciousness. The notion of the brain as a quantum computer invites us to reimagine our understanding of consciousness and the mind. Just as the intricate forest represents the complexity of neural networks, the potential for quantum processes within the brain suggests that our thoughts may traverse uncharted paths of possibility. As we stand on the brink of discovery, exploring the interplay between quantum mechanics and the brain opens up new avenues for understanding who we are and how we think. While the journey is fraught with uncertainty and challenges, it is also rich with the promise of unlocking the secrets of consciousness, inviting us to embrace the mysteries that lie within the very fabric of our being. Quantum consciousness. In the dimly lit halls of scientific inquiry, two seemingly disparate realms have long occupied the minds of thinkers: the quantum world of subatomic particles and the intricate tapestry of human consciousness. What if these two worlds are more closely intertwined than we ever imagined? This audacious question lies at the heart of the concept of quantum consciousness, a field that explores the intersection of quantum mechanics and our understanding of the mind. To embark on this exploration, let's first step into the quantum realm, a world governed by probabilities rather than certainty. Picture a tiny particle like an electron darting around in unpredictable patterns, existing in a state of superposition. This means that until observed, it can be in multiple states simultaneously. It's akin to a coin spinning in the air, existing as both heads and tails until it lands and is observed. This strange behavior, which defies our everyday experience, hints at a reality that is far more complex and interwoven than we typically perceive. Now, let's pivot to consciousness. What is it that makes us aware, that allows us to ponder our existence and perceive the world around us? For centuries, philosophers, scientists, and mystics have sought to define consciousness. often viewing it as an emergent property of complex biological systems. But what if consciousness is not merely a product of classical processes in the brain, but is instead rooted in the quantum domain? This idea has intrigued theorists like physicist Roger Penrose and anesthesiologist Stuart Hameroff, who propose that consciousness arises from quantum processes occurring within neurons. Imagine a symphony orchestra where each musician represents a neuron firing in the brain. In this analogy, the music is the manifestation of consciousness, a beautiful harmony resulting from the precise coordination of countless individual notes. However, what if the musicians were not just playing in a traditional sense, but instead were tapping into an ethereal realm of possibility, drawing upon the rich tapestry of quantum potentiality? This concept suggests that the brain might serve as a conduit for quantum information, weaving together the threads of reality in ways we are only beginning to comprehend. One of the cornerstones of this theory is the notion of coherence. In the quantum realm, particles can exist in a state of coherence, where they maintain a synchronized relationship, allowing for the sharing of information across distances. This idea resonates with how consciousness seems to transcend the limitations of space and time, allowing for intuition, creativity, and even moments of sudden insight. Could it be that our minds tap into a deeper quantum field, accessing information beyond the conventional flow of time and space? Yet, the implications of quantum consciousness extend beyond mere theoretical musing. They touch on profound questions about the nature of reality itself. If consciousness arises from quantum processes, it challenges our understanding of free will and determinism. Are our thoughts and decisions merely the result of classical neuronal activity? Or do they arise from a more complex interplay with the quantum fabric of the universe? This inquiry evokes echoes of philosophical debates that have persisted for centuries as we grapple with the implications of a mind that might be intricately linked to the fundamental workings of reality. Consider the phenomenon of entanglement, a core principle in quantum mechanics, where particles become interconnected, such that the state of one instantaneously influences the state of another, regardless of the distance separated. This concept not only raises eyebrows in the realm of physics, but also provokes intriguing parallels in consciousness. Could our thoughts and emotions be entangled with one another, bridging distances between minds, suggesting a shared collective consciousness that transcends individual experience? As we delve deeper into the enigma of quantum consciousness, we encounter fascinating experiments that hint at the interplay between the mind and the quantum world. For instance, researchers have investigated how conscious observation can influence the behavior of quantum particles, suggesting that the act of observation may play a crucial role in shaping reality. This phenomenon raises questions about the role of the observer, blurring the lines between subject and object, and inviting us to reconsider our place in the universe. Our journey into quantum consciousness not only opens a window into the fundamental workings of reality, but also invites us to explore the very essence of what it means to be human. Through the lens of quantum mechanics, we may find ourselves contemplating the nature of awareness, the fabric of existence, and the profound interconnectedness of all things. Panpsychism. The idea that consciousness pervades the universe. Imagine looking at a tree, feeling the breeze, or gazing up at the stars. What if all these things, trees, air, and even the distant stars, had some form of consciousness? This is the intriguing idea behind panpsychism, the philosophical view that consciousness is not something unique to humans or animals, but a fundamental feature of the universe itself. According to this theory, consciousness is present in all things, from the smallest particles to the largest galaxies in some basic form. It's a mind-bending idea that upends the traditional view that consciousness is a rare, complex phenomenon only found in brains. Instead, panpsychism suggests that consciousness is woven into the fabric of reality, just like space, time, and matter. What is panpsychism? The term panpsychism comes from the Greek words pan, meaning all, and psyche, meaning soul or mind. It's an ancient idea dating back to pre-Socratic philosophers like Thales, who believed that even inanimate objects like stones or rivers might possess a form of life or spirit. However, in modern times, panpsychism has gained new attention as philosophers and scientists struggle with one of the hardest problems in science, the nature of consciousness. At its core, panpsychism is the idea that everything in the universe has a form of consciousness, or at least a proto-consciousness, that exists on a continuum. In humans, this manifests as the rich, complex experiences we associate with consciousness: thoughts, emotions, self-awareness. In simpler entities like animals, plants, or even atoms, this consciousness might be vastly simpler, perhaps just a basic capacity to respond to stimuli. One of the most important aspects of panpsychism is that it doesn't necessarily attribute human-like consciousness to everything. A rock or an electron doesn't think or feel like we do, but it might have a very basic form of awareness or experience that contributes to the larger tapestry of consciousness in the universe. The hard problem of consciousness. Panpsychism is often discussed in relation to the hard problem of consciousness, a term coined by philosopher David Chalmers. The hard problem refers to the difficulty of explaining how and why we have subjective experiences, why there is something it is like to be you, to see colors, to feel pain, or to enjoy music. Neuroscientists can describe the brain in terms of neurons firing and chemicals moving around, but this doesn't explain why certain brain processes result in conscious experience. This is where panpsychism comes in. One of the main appeals of panpsychism is that it offers a solution to the hard problem. If consciousness is a fundamental feature of the universe, like mass or charge, then we don't need to explain how consciousness emerges from non-conscious matter. Instead, consciousness is simply another basic property of reality, and the complex consciousness we experience as humans is built up from the simpler forms of consciousness present in all things. Panpsychism versus materialism. Panpsychism challenges the dominant philosophical view in science known as materialism. Materialism holds that everything in the universe is made of matter, and that consciousness is something that emerges from particular arrangements of matter, like neurons in a brain. According to materialism, consciousness only appears in complex systems, and before the development of brains, there was no consciousness in the universe. Panpsychism flips this idea on its head. Instead of viewing consciousness as something that appears only in complex systems, panpsychism suggests that consciousness is already present in the simplest components of the universe. When these components come together in a brain, they don't create consciousness from scratch. They combine their already existing consciousness into something more complex. This idea may sound strange, but some philosophers argue that it actually solves several problems that materialism struggles with. One problem with materialism is that it has a hard time explaining how unconscious matter, like atoms or molecules, can give rise to conscious experience. Panpsychism avoids this issue by asserting that matter was never unconscious to begin with. It has always had a form of proto-consciousness, the combination problem. One major challenge for panpsychism is known as the combination problem. If everything in the universe has a form of consciousness, how do these individual bits of consciousness combine to form the unified, complex consciousness that we experience as human beings? How do the experiences of individual atoms in your brain, for example, combine to create the rich, unified experience of being you? Some critics argue that panpsychism doesn't solve the hard problem of consciousness, it just shifts it to a different level. Instead of explaining how consciousness emerges from matter, panpsychism now has to explain how small consciousnesses combine to form bigger ones. Panpsychists have proposed different answers to this problem. Some suggest that consciousness operates according to principles that we don't yet understand, while others argue that our conception of consciousness may need to be revised to accommodate these ideas. Modern support for panpsychism. In recent years, panpsychism has attracted renewed interest from both philosophers and scientists. This is partly because the traditional materialist approach has struggled to explain consciousness in satisfactory terms. While neuroscience can describe the mechanisms of the brain in incredible detail, it still doesn't provide an answer to the question of why certain brain processes result in the subjective experience of being conscious. Prominent philosophers like Galen Strawson and Philip Goff have advocated for panpsychism as a viable theory of consciousness. They argue that the simplicity and elegance of the idea make it worth considering, especially when compared to materialism, which struggles to account for the subjective nature of consciousness. There's even a growing movement within physics to explore the connections between panpsychism and quantum mechanics. Some interpretations of quantum theory suggest that consciousness may play a fundamental role in the behavior of particles, lending support to the idea that consciousness could be a basic feature of the universe. Conclusion: a universe alive with awareness. In the panpsychist view, the universe is not a cold, dead mechanism of mindless matter. Instead, it is alive with consciousness in varying degrees of complexity. From the tiniest subatomic particles to the vastest galaxies, everything participates in this great web of awareness. It's a view that offers a radically different perspective on the nature of reality, one in which we, as conscious beings, are deeply connected to the rest of the cosmos, not just through physical laws, but through shared experience and awareness. Panpsychism invites us to reimagine the universe not as a collection of inert objects, but as a vast, interconnected system where consciousness pervades everything. It raises profound questions about what it means to be conscious and challenges our understanding of what it means to exist in a universe that might be far more alive than we ever imagined. Biocentrism. Biocentrism is a radical theory proposed by Robert Lanza, a prominent scientist in the fields of biology and regenerative medicine, that challenges the traditional views of the universe and reality itself. At its core, biocentrism suggests that life and consciousness are not mere byproducts of the cosmos, but are central to its existence. In other words, rather than consciousness arising from matter, it is consciousness that gives rise to matter, and the very fabric of space and time. This theory turns conventional understanding of reality on its head. In the standard materialistic view of the universe, the physical world exists independently of the observer, and human consciousness is seen as a latecomer in the evolutionary story, emerging from complex biological processes over time. But in biocentrism, consciousness plays the primary role in shaping the world around us. The universe does not exist out there, in some objective independent state. Instead, the universe is brought into being by our observations and experiences. To understand how biocentrism works, we need to examine some peculiar aspects of quantum mechanics. One of the most well-known phenomena in quantum physics is the observer effect. This is the idea that the act of observing a quantum system, such as a photon or an electron, actually influences the state of that system. Before an observation is made, quantum particles exist in a state of superposition, meaning they can be in multiple states at once. However, the moment we measure or observe them, they collapse into a definite state. This strange behavior has puzzled scientists for decades, leading to profound philosophical debates about the nature of reality. Biocentrism seizes upon this observer effect to argue that consciousness plays a direct role in shaping the physical world. According to biocentrism, without a conscious observer, the universe would exist in a kind of indeterminate haze of possibilities. It is our consciousness that brings the universe into focus, giving it form and substance. In traditional physics, space and time are seen as fundamental components of the universe, existing independently of life or consciousness. But biocentrism offers a different perspective. Lanza argues that space and time are not objective realities, but constructs of the mind. They are the mental frameworks we use to organize our experiences. In essence, they are part of the toolkit that consciousness uses to interpret the raw data of existence. Imagine space and time as the stage upon which all events unfold. According to biocentrism, that stage is not a fixed entity that exists outside of our awareness. Instead, it is more like a virtual reality environment generated by our minds to make sense of the sensory information we receive. Just as a computer game creates a 3D world for the player, our consciousness creates the dimensions of space and time to give context to our experiences. This perspective draws from the idea of relativity. In Einstein's theory of relativity, time and space are not absolute. They can be stretched or contracted depending on the observer's speed and position. Biocentrism takes this a step further by claiming that without a conscious observer, there would be no space or time at all. The universe, in its essence, is a formless state of potential that consciousness sculpts into reality. As a biologist, Lanza places life at the center of his theory. He argues that most cosmological theories overlook the role of light in shaping the universe. According to biocentrism, light is not a mere byproduct of physical processes in a dead universe. Instead, light is fundamental to the very existence of the cosmos. The theory suggests that biology, not physics, is the key to understanding the universe. One way to understand this is through an analogy with a video game. In a video game, the virtual world is built from lines of code, and it remains dormant until a player interacts with it. Similarly, in biocentrism, the universe is a kind of cosmic code that remains potential until light interacts with it. Our biological processes, particularly consciousness, are what activate the universe, bringing it to life. Biocentrism challenges us to rethink many of the assumptions we take for granted about the universe. For example, consider the famous question: if a tree falls in the forest and no one is there to hear it, does it make a sound? According to biocentrism, the tree, the sound, and even the forest itself might not exist in any meaningful way without an observer. The tree would only exist as a probability until consciousness interacts with it, bringing it into reality. This theory also raises profound questions about death and the nature of existence. If consciousness plays a central role in creating reality, what happens when we die? Does the universe cease to exist for us, or does consciousness persist in some form, creating new realities? Lanza speculates that death may not be the end of consciousness, but merely a transition to another state of awareness, where new experiences and new universes are created by the mind. Biocentrism is a bold and revolutionary idea that challenges the materialist assumptions that have dominated science for centuries. It suggests that light and consciousness are not passive products of the universe, but are active participants in shaping it. By placing consciousness at the center of the equation, biocentrism offers a new way of understanding the cosmos, one in which the mind is not just a latecomer, but a fundamental force that brings reality into being. Whether or not biocentrism holds the key to unlocking the mysteries of existence, it forces us to reconsider the role of light and consciousness in the grand cosmic scheme, opening the door to deeper philosophical and scientific explorations. Emergence theory. Emergence theory is one of the most fascinating and far-reaching ideas in both science and philosophy. At its heart, it suggests that complex systems and patterns can arise out of the interaction of simple elements in ways that are not easily predictable or reducible to the behavior of those individual parts. It challenges our traditional understanding of how systems work by showing that sometimes the whole is indeed much greater than the sum of its parts. Let's begin with a simple analogy to understand this concept. Consider a flock of birds. Individually, each bird follows a relatively simple set of rules. Maintain a certain distance from its neighbors, align with the direction of others, and avoid obstacles. However, when you look at a flock in motion, what you see is a complex, coordinated dance. The flock moves as if it were a single organism, changing direction, diving, and soaring in perfect sync. No single bird is in charge of this, but through their individual actions, an emergent pattern appears, something that no individual bird could produce on its own. This is the essence of emergence, complex behavior arising from simple rules without central control. It's an idea that applies not only to flocks of birds, but to many other systems in nature, from the way ants build colonies, to how neurons in our brain give rise to consciousness. Emergence theory suggests that certain properties, structures, and behaviors only become apparent when you have enough interacting components, and that these emergent properties are not easily understood by just examining the components in isolation. In physics and cosmology, emergence plays a significant role. Consider temperature. While it's easy to measure, temperature is not something that exists at the level of individual molecules. It only becomes meaningful when you have a large number of particles interacting, their collective kinetic energy giving rise to the concept of temperature. The same applies to fluid dynamics. The notion of a wave doesn't make sense when looking at individual water molecules, but once you have enough molecules, the wave is an emergent property of their collective behavior. One of the most captivating examples of emergence comes from the field of biology. Think about life itself. At the molecular level, life is built from protein, nucleic acid, and other chemicals. None of these chemicals, on their own, are alive. But when they come together in the right way, life emerges. cells grow, metabolize, reproduce, and evolve. The question of how life emerges from non-living matter is still one of the great mysteries of science. But emergence theory provides a framework for understanding how such a complex dynamic system could arise from simpler components. Emergence is also at the heart of consciousness, one of the most profound philosophical questions. How does subjective experience arise from the activity of neurons? Our brains are made up of billions of neurons, each of which is a relatively simple biological unit that fires or doesn't fire based on electrical and chemical signals. Yet somehow, from the interaction of all these neurons, consciousness emerges. We don't fully understand how this happens, and some argue that consciousness is an irreducible phenomenon, an emergent property that cannot be fully explained by simply breaking it down into its constituent parts. In recent years, emergence theory has also been applied to the realm of cosmology, particularly in theories about the nature of space and time. Some physicists believe that space and time themselves might be emergent properties, not fundamental aspects of the universe. In this view, at the most fundamental level, the universe could be made of something entirely different, and space-time might emerge from the interactions of more basic elements, perhaps quantum information or something even more abstract. One area where emergence theory is actively being explored is in understanding the origin of the universe. The Big Bang theory describes the universe's expansion from a hot, dense state, but it doesn't fully explain why the universe has the structure it does, or why certain physical constants appear to be fine-tuned for life. Some researchers believe that these properties of the universe might be emergent, arising from underlying rules that we have yet to fully understand. The idea of emergence raises philosophical questions as well. If emergent properties can't be reduced to their components, does that mean the universe has a kind of built-in creativity, or unpredictability? Could the rules that govern the universe be capable of generating entirely new forms of complexity over time? And if so, what does that say about the nature of reality? Emergence also has implications for how we understand causality. In classical physics, the behavior of a system can be predicted if we know the properties of its part. But in emergent systems, the behavior of the whole is often more than just the sum of its parts. This raises questions about determinism. If complex, unpredictable behaviors can emerge from simple rules, does that mean the universe is inherently unpredictable in some ways? One of the most famous examples of this unpredictability is in chaos theory, which studies how small changes in a system can lead to vastly different outcomes. The classic example is the butterfly effect, where the flap of a butterfly's wings in Brazil could set off a chain of events that leads to a tornado in Texas. In emergent systems, small initial conditions can give rise to entirely new patterns of behavior. In summary, emergence theory is a powerful framework for understanding how complexity arises from simplicity. It helps explain phenomena across multiple disciplines, from physics and biology to consciousness and cosmology. By recognizing that complex behaviors and properties can emerge from the interactions of simpler parts, emergence theory challenges traditional reductionist approaches and opens up new ways of thinking about the universe. It suggests that the world we observe is shaped not just by the fundamental building blocks of matter, but by the dynamic, creative interplay of those parts, leading to systems that are greater than the sum of their components. Morphic resonance. Morphic resonance is a highly unconventional theory proposed by biologist Rupert Sheldrake, which challenges many of the core assumptions of mainstream science. At its heart, morphic resonance suggests that the forms and behaviors of living organisms are not solely determined by genetic information or environmental factors, but also by a kind of collective memory. This memory is shared across species and even across time, allowing past forms and behaviors to influence present ones. In this view, nature is not just a mechanical system operating under fixed laws, but a dynamic process influenced by the habits of the past. To understand morphic resonance, it's helpful to start with Sheldrake's critique of traditional science, particularly the mechanistic view of biology. In the standard model, organisms develop according to a fixed blueprint encoded in their DNA. This genetic information, combined with environmental influences, is thought to explain everything from the shape of an animal's body to its instincts and behaviors. But Sheldrake argues that this view is incomplete. He suggests that there is something missing from our understanding of how organisms take their form and exhibit complex behaviors. Sheldrake's radical alternative is the idea of morphic fields. A morphic field is a non-physical field that contains the pattern for a particular structure or behavior. These fields are not just abstract concepts, but are thought to be real, though invisible, organizing principles that shape everything in the natural world, from the way crystals form to the way birds migrate. The key point is that morphic fields carry a kind of memory or resonance from previous instances of similar structures or behaviors. Here's where the concept of resonance comes in. According to Sheldrake, once a particular form or behavior has occurred, it becomes easier for that same form or behavior to happen again in the future. This is because the morphic field for that form or behavior has been strengthened by previous instances. In essence, the past exerts an influence on the present, not through genetic inheritance or environmental condition, but through resonance with a field that contains the memory of similar events. This is the process of morphic resonance. A common analogy used to explain morphic resonance is learning. Imagine you're trying to solve a puzzle for the first time. It might take you a long time to figure it out, and you might make mistakes along the way. But once you've solved it, solving it again becomes much easier. Sheldrake extends this analogy to the natural world, suggesting that when one member of a species learns a new behavior or develops a new trait, it becomes easier for other members of that species to do the same, even if they're far away and have no direct contact with the original learner. This idea becomes even more fascinating when applied to complex behaviors, such as the way birds migrate or the way termites build elaborate mounds. According to morphic resonance, these behaviors are not just encoded in the DNA of individual organisms, but are also influenced by the collective memory of the species. Each time a bird successfully completes its migration, it strengthens the morphic field for that behavior, making it easier for future generations of birds to follow the same rule. Sheldrake has proposed experimental evidence to support morphic resonance. One example comes from research on rats learning to navigate mazes. In these studies, rats in different locations were trained to solve a maze, and subsequent generations of rats were able to learn the maze faster than the previous generation. Sheldrake interpreted this as evidence of morphic resonance at work. The collective memory of the rats that had already solved the maze was influencing the behavior of rats that had never encountered it before. However, it's important to note that morphic resonance remains highly controversial within the scientific community. Critics argue that there is no rigorous empirical evidence to support the existence of morphic fields or the process of morphic resonance. They contend that the phenomena Sheldrake describes can be explained by more conventional means, such as social learning, genetic predisposition, or environmental influence. Many scientists see morphic resonance as a speculative hypothesis that lacks the predictive power and falsifiability required of a scientific theory. Yet, despite the skepticism, Sheldrake's theory continues to attract attention, partly because it challenges the reductionist approach of modern science. In a world dominated by materialistic explanations, morphic resonance offers a more holistic perspective. It suggests that there may be organizing principles in nature that we don't yet fully understand, principles that transcend the boundaries of space and time. For some, this is a liberating idea, opening the door to new ways of thinking about consciousness, evolution, and the interconnectedness of all living things. One of the reasons morphic resonance is so compelling to many is that it resonates, pun intended, with intuitive notions of interconnectedness that are found in many ancient philosophies and spiritual traditions. For instance, the idea that there is a memory in nature, or that the past influences the present in non-linear ways, can be found in concepts like the Akashic records in Eastern traditions, or the idea of collective unconscious in Jungian psychology. In the end, whether or not morphic resonance will ever be accepted by mainstream science, it serves as a provocative reminder that our understanding of the natural world is still incomplete. Sheldrake's work encourages us to remain open to the possibility that there may be unseen forces at play in the cosmos, shaping the patterns of life in ways that challenge our current scientific paradigms. The Omega point The concept of the omega point is a fascinating blend of cosmology, theology, and philosophy, first introduced by the Jesuit priest and paleontologist Pierre Teilhard de Chardin. At its core, the omega point theory suggests that the universe is not merely a physical system winding down toward entropy and heat death, but rather it is moving toward an ultimate transcendent point of convergence. This convergence, the omega point, represents the culmination of all complexity, consciousness, and order in the universe into a unified state, often interpreted as a divine or superconsciousness. Imagine the universe as a kind of grand narrative. Teilhard de Chardin believed that this narrative had a direction, a vector that was not random but purposeful. The evolution of the cosmos, from the formation of stars and galaxies to the emergence of life and human consciousness, was, in his view, part of a larger teleological process. Each step forward in complexity, from atoms to molecules, from single-celled organisms to multicellular life, and from primitive consciousness to human awareness, was a sign of this progression toward greater complexity and unity. The final stage in this process is what Teilhard termed the omega point. One way to grasp the idea is through analogy. Picture a sphere expanding in all directions, yet with all points on its surface being drawn inexorably toward a single point at its center. The surface of the sphere represents the unfolding of complexity and consciousness throughout the universe, while the center represents the omega point. As the sphere grows, the universe becomes more complex and conscious, but at the same time, everything is being drawn toward this final moment of unity. Teilhard's vision was deeply rooted in his Christian faith, and he equated the omega point with Christ, the alpha and omega of existence. However, his theory also appealed to broader spiritual and scientific imaginations, because it presented a hopeful, progressive view of the universe. Instead of seeing the universe as entropic and doomed to decay, Teilhard proposed that the ultimate fate of the universe was to culminate in a divine, hyperconscious state. From a scientific perspective, Teilhard's idea can be framed in more abstract, non-religious terms. The omega point can be viewed as the ultimate destination of evolution, not just biological evolution, but cosmic evolution itself. It is the idea that the universe is a system that moves from chaos toward greater levels of order and self-organization. In a sense, it is the opposite of entropy, which suggests a movement from order to disorder. Instead, the omega point theory posits that complexity and consciousness continue to evolve and grow, driving toward a state where all of existence reaches its highest potential. One modern thinker who has expanded on Teilhard's omega point concept is the physicist and cosmologist Frank Tipler. Tipler's version of the omega point is rooted in theoretical physics, and he uses the framework of general relativity and quantum mechanics to argue that the universe could evolve in such a way that it leads to infinite computational power and complexity. Tipler imagines a future where, as the universe approaches its final state, a potential big crunch or singularity, advanced civilizations could use this infinite computational power to simulate all of reality, effectively creating a kind of eternal life for all conscious beings. This interpretation of the omega point is far more technical, but it shares Teilhard's view that the universe is moving toward a transcendent, final state. However, despite its visionary nature, the omega point theory is not without its critics. Many scientists point out that the universe seems more likely to end in heat death, an entropic state of maximum disorder where all energy is evenly distributed and no work can be done. This scenario is the antithesis of the omega point, as it suggests that the universe will eventually become a cold, lightless void, with no possibility of further complexity or consciousness. Teilhard's response to this entropic view would likely be that physical science, while insightful, does not capture the full picture of reality. For Teilhard, consciousness and spirit are real forces in the universe, just as real as gravity or electromagnetism. He believed that while matter might seem to wind down according to physical laws, consciousness could still evolve toward higher and more unified states. The omega point, therefore, is not merely a physical event, but also a metaphysical one, transcending the limitations of material existence. This brings us to a key philosophical dimension of the omega point, the relationship between matter and consciousness. Teilhard argued that matter and consciousness are not separate, but two aspects of the same reality. As the universe evolves materially, it also evolves spiritually. In other words, the emergence of consciousness is not an accident of biological evolution, but an intrinsic part of the cosmic process. The omega point, therefore, represents not just the culmination of physical evolution, but also the full realization of consciousness, perhaps even a state where individual consciousnesses merge into a collective or universal consciousness. In some ways, the omega point theory resonates with ideas from Eastern philosophies, such as the concept of Brahman in Hinduism, or the idea of nirvana in Buddhism. Both of these concepts refer to an ultimate transcendent state of being, where the individual self is absorbed into a larger universal whole. While Teilhard's omega point is framed within a Christian context, its echoes can be found in many spiritual traditions that see the universe as moving toward a final harmonious state. Ultimately, the omega point is a visionary theory that invites us to reconsider the nature of evolution, consciousness, and the universe's ultimate fate. It offers a counterpoint to the pessimistic view of a universe doomed to decay and extinction, suggesting instead that we are part of a grand, purposeful cosmic journey. Whether one interprets the omega point as a scientific possibility, a spiritual truth, or a poetic metaphor, it challenges us to think about the universe as more than just a collection of particles and forces, but as a living, evolving system moving toward its greatest potential. Anthropic principle. The anthropic principle is one of those philosophical and scientific ideas that quietly reshapes how we think about the universe and our place within it. On the surface, it asks a deceptively simple question. Why does the universe appear to be so perfectly tuned for life, and in particular human life? Dig deeper, and it forces us to confront profound questions about the nature of existence, cosmology, and the role of consciousness in the universe. At its core, the anthropic principle is about explaining the apparent fine-tuning of the universe. When we observe the physical constants and laws of nature, things like the strength of gravity, the charge of the electron, or the expansion rate of the universe, we notice that they fall within very narrow ranges that allow life, at least life as we know it, to exist. If any of these constants were even slightly different, the universe could have been a vastly different place, one where galaxies, stars, planets, and light would not form. Let's put it into a simple analogy. Imagine you walk into a room where a giant roulette wheel is spinning. The wheel has millions of tiny slots, each corresponding to a different set of physical laws and constants. As the wheel slows down, it lands precisely on one of the slots that allows for life. The question the anthropic principle raises is it just a lucky coincidence that the wheel stopped on a life-permitting slot? Or is there something deeper at work? There are two major formulations of the anthropic principle, the weak anthropic principle and the strong anthropic principle. The weak anthropic principle, PP, is in some sense the least controversial. It simply states that we shouldn't be surprised that we observe a universe fine-tuned for life, because if the universe weren't suited for life, we wouldn't be here to observe it. In other words, the conditions of the universe must allow for the observer's existence. It's a tautology. Life exists in the universe because the universe allows life to exist. For example, imagine you're standing on Earth, marveling at how it's the perfect distance from the sun to support life. According to the weak anthropic principle, this is not a surprising observation, because if Earth weren't in this Goldilocks zone, not too hot, not too cold, you wouldn't be standing there thinking about it. This formulation of the principle is sometimes seen as more of a clarification than an explanation, but it still has important implications. It reminds us that our perspective as observers is necessarily biased. We can only observe conditions compatible with our existence. The strong anthropic principle, SAP, on the other hand, takes things a step further. It suggests that the universe must have the properties that allow life to develop. In other words, the universe is not just randomly fine-tuned for life. It is somehow compelled to be that way. The SAP opens the door to a more teleological view of the cosmos, hinting that life, and maybe even consciousness, is not just a fortunate accident, but an integral part of the universe's structure. Some proponents of the strong anthropic principle argue that life is the universe's way of knowing itself. From this perspective, human consciousness and intelligence are not just side effects of cosmic evolution, but central features of the universe's design. In this sense, the anthropic principle doesn't just explain why the universe supports life. It raises the possibility that life and consciousness are the ultimate goals of the universe. Now, one of the most interesting implications of the anthropic principle is how it intersects with the idea of the multiverse. If we imagine that our universe is just one of a potentially infinite number of universes in a vast multiverse, then the fine-tuning problem becomes less mysterious. In a multiverse with every possible set of physical laws and constants, there would inevitably be at least some universes where the conditions are just right for life. The fact that we happen to live in one of those universes is no more surprising than finding yourself living on a planet like Earth. It had to be this way for us to exist. To illustrate, let's return to the roulette wheel analogy. Imagine instead of just one wheel, there are countless wheels, each corresponding to a different universe. Some wheels land on universes where life is impossible, where gravity is too weak, or the cosmological constant is too strong, causing the universe to tear apart before galaxies can form. But some wheels land on universes where the conditions are just right. In a multiverse with infinite rolls of the dice, the odds of at least one life-permitting universe being realized are inevitable. However, not everyone is satisfied with the multiverse explanation. Some argue that invoking a multiverse to explain the fine-tuning of our universe is like explaining one mystery by introducing an even bigger one. After all, how do we prove that a multiverse exists? Moreover, the strong anthropic principle still lingers in the background, suggesting that perhaps the universe is designed for life in a more fundamental way, whether or not there are multiple universes. Philosophically, the anthropic principle touches on the age-old debate between randomness and purpose. Is the universe just a random, purposeless accident, where life is an unlikely but inevitable outcome in one of countless possible universes? Or is there a deeper reason why the universe is of the way it is, something that points to purpose, design, or even consciousness being woven into the fabric of reality?